Welcome. My name is Andy Kuszak. I have a Superior inspection in Northwest Arkansas. I've been in construction most of my adult life in one form or another, and I got into home inspecting about 8 years ago, coming from commercial construction. And I really fell in love with the industry and everything it had to offer. And so I started getting involved in teaching my home inspectors, and it's kind of led me to InterNACHI and opportunities that they have helped me with. So, all right, a little bit about me. I guess now let's go to the course. All right, so I think we already went through, AJ already went through some of this. New York inspectors, within 48 hours of the conclusion of this, please send Kayla your info. All inspectors, you must be present at least 90%. And the entire course was pre-approved by your specific state, if so, and based on the IRC and the NEC. So definitely your AHJ may be different. So just please keep that in mind as we go through this info. On average, we have about one slide per minute, and we're already a little behind. So just bear with me. We have a lot of information to cover. So, all right, first things first, this is not a code course. This course is designed to help the student understand some, but not all, electrical installations. Local codes and building standards may have exceptions to the content presented in this course. And let me get out of something. Okay, there we go. All right. There we go. Move some of this stuff over. Okay. So first things first, safety. Obviously, electricity kills. So the primary responsibility of a home inspector when inspecting electrical systems and components during a home inspection is the safety of the inspector's clients, and the building occupants. Built to code. This is one of the few areas that most home inspectors would report as in need of correction. Systems or components that may have been acceptable or built to code when the home was built, but now may be considered defective or unsafe. An absence of GFCI in the kitchen, for example, would fall into this category. Many home inspectors inspect the home or building without regard to when the home was built. Next is primary safety. The home inspector should be especially cautious when evaluating panel boards. An electrical system and distribution panel can kill a person. According to the InterNACHI Home Inspection Standards of Practice, a home inspector is not required to do anything that the home inspector thinks is unsafe, including removing dead fronts from the electrical cabinets or panel boards and exposing electrified, live, or hot electrical components within. Stay safe during a home inspection. Do not endanger yourself or others. Use personal protective equipment and take InterNACHI's free online safe practices for the home inspector course. And then standards of practice. Be sure to refer to the standards of practice and read the requirements and exclusions for conducting the electrical inspection of a home or building. According to InterNACHI Home Inspection's standards of practice, the inspector is required to inspect the service entrance conductors, the main service disconnect, panel boards, overcurrent protection devices, circuit breakers and fuses, and service grounding and bonding. The home inspector is not required to remove the panel board cabinet covers or dead fronts. All right. A home inspector is not required to remove the dead front cover from an electrical panel board cabinet enclosure or box. The image above is of a dead front and door of a panel board. Removing it is hazardous. InterNACHI does not require and does not recommend home inspectors to remove the dead front. If in any doubt about anyone's safety, defer the inspection to a licensed electrical contractor. Inspectors should follow these basic safety rules when inspecting live electrical components. Wearing protective eyewear and gloves, removing electrical components from your body, do not wear nylon or polyester clothing, so on and so forth. Basic terms. Using the correct terminology. One of the challenges facing home inspectors during the electrical portion of a home inspection is getting the terminology right. Many home inspectors end up looking inexperienced or unprofessional by not knowing the correct verbiage. For example, a wire is more properly called a conductor. There, you can always refer to the InterNACHI glossary of home inspection terms for a more thorough list. But here are some commonly used terms and their correct usage. Understanding these terms will help the inspector recognize improper wiring, especially in the case of grounded and ungrounded conductors. Ampacity, appliance, AFCI, AWG, meaning American wire gauge, bonded, branch circuit, cabinet, circuit breaker, current, dead front, device, disconnecting means, feeder, GFCI, hot wire, line, load, main breaker, meter, and neutral wire. You can see in this diagram on the right-hand side of the screen, the equipment grounding conductor, the EGC, may be commonly referred to as the grounding conductor, the grounded conductor, grounding conductor, or the ground wire. The equipment grounding conductor is the green or bare copper wire. It is not intended to carry current except in case of a ground fault. The image above shows some common wires with the ground wire as the bare copper conductor image. Another term is service entrance conductor, or SE cables. SER and SEU are two common types of SE cables. SER refers to a 3-wire, or I'm sorry, the image above shows an SEU, so SER is a 3-wire, SEU is a 2-wire. Outlet. Other terms that we're looking for is overcurrent protection device, panel board, receptacle, receptacle outlet, Romex, service, and then obviously the SEU and SE and SEU. All right. All right. Nomenclature and abbreviations. There are several different ways to refer to the size of wire. And the way that it's abbreviated also. So you have 4 AWG. It's also referred to as number 4, the abbreviation number and 4, and then 4 AWG, and then 4 gauge. Same thing with the larger gauges. You have triple aught, so 3-aught, 3 AWG, and then the 000 and then 3-0 all refers to the same type of stuff. Common wires used in electrical power distribution in homes can be identified by a wire size followed by the number of wires used in the cable assembly. The most common type of distribution cable, NMB, is generally referred to in 3 different ways: 14-2, 12-2, and 10-3. AWG is colloquially referred to as gauge, and the zeros in large wires are referred to as aught. A wire that is sized 1 AWG is referred to as 1 gauge or number 1 wire. Similarly, smaller diameters are referred to in gauge or number gauge wire, where X is the positive integer, AWG. Consecutive AWG wires, wire sizes larger than number 1 are designated by number of zeros. So 1-aught, 2-aught, 3-aught. Getting the terminology right will avoid a lot of "your inspector doesn't know what he's talking about" comments from the local electrical contractors. Let's see. To understand power, understanding how electricity works. Electrical current is actually the movement of electrons flowing along a conductor in much the same way as water flows through a pipe. The same fundamental principles apply in the same way. The bigger the pipe, the more flow it can handle. Conversely, smaller pipes can handle small supplies. This is the principle behind resistance. An analogy to understanding electricity is a water pipe, where the voltage is the water pressure, the current is the flow rate, and the resistance is the size of the pipe. Current, the flow rate or amps, is equal to the voltage, water pressure or volts, divided by resistance, which is the size of the pipe or the ohms. Let's see how this relation applies to the plumbing system. Assume you have pressurized water coming out of a garden hose. When you increase pressure, more water comes out of the hose. Similarly, in an electrical system, when you increase voltage, the current increases. Now assume you increase the diameter size of the garden hose. More water will come out of the hose. Similarly, when you decrease the resistance in an electrical system, the current flow increases. And then power. Electrical power is measured in watts. In an electrical system, power or watts is equal to voltage multiplied by current. And then measuring electrical forces. When discussing electrical supply, we use many different terms to quantify the amount of available power, the amount of work it can do, the resistance of the components, and therefore its safe operating parameters. Here are some easy to understand definitions and explanations of the terminology. Resistance is limits the conductor's ability to allow the flow of electrons, just as friction causes losses in pipe or ductwork. This is expressed in ohms. Electrical force is what drives electrons along the conductor and is expressed as voltage or volts. Current is the flow of electrons driven by electromotive force through a given resistance. This is expressed as amps. And power is the amount of work that the electrical flow can do. This is expressed as watts or kilowatts. Ohm's law. Ohm was able to define the fundamental relationship between voltage, current, and resistance. These fundamental relationships are of such great importance that they represent the true beginning of electrical current analysis. Unfortunately, when Ohm published his findings in 1827, his ideas were dismissed by his colleagues. Ohm was forced to resign from his high school teaching position and lived in poverty and shame. However, his research efforts gained a lot of support outside Germany. In 1849, George Simon Ohm was officially recognized for his efforts by being appointed as professor of the University of Munich. How do Ohm's laws help us? Ohm's laws are basically a series of mathematical models that show us how to work out safe working loads for conductors and electrical components. This allows us to understand why, for example, a 30 amp fuse should not be connected to a 14 AWG wire. That's about resistance overheating wires. Ohm's laws define the relationship between voltage, current, and resistance, where I is the current measured in amps, R is the resistance measured in ohms, and E is the electrical potential voltage, and W is power measured in watts. Amps measure current, the volume of the current, the number of electrons flowing past a given point per second is measured in amperes or amps. Volts measure pressure. The pressure under which electricity moves is measured in volts. Electricity arrives at household circuits at a pressure of 120 or 240 volts. And watts measure power. Power is measured in watts, and you can compute wattage by multiplying amps and volts. All right, understanding the limitations of a conductor. As we saw with Ohm's law, resistance is the key to a conductor's ability to safely deliver the amount of power that a circuit needs. Think back to the pipe. The bigger the pipe, the lower the resistance. Conductor material. When evaluating electrical supply, we need to recognize that copper and aluminum conductors are not the same. Although they are both commonly used in residential supply, copper inherently has less resistance to the flow of electrons than aluminum does. For this reason, aluminum conductors are always 1 or 2 sizes larger than the equivalent copper one for any given amperage. And speaking of aluminum, single strand or solid aluminum branch circuit wiring should always be fully evaluated by a licensed electrical contractor. Multi-strand aluminum wires, as seen on service entrances in high amperage circuits, are not a problem. This issue is presented in more detail later. Large conductor size, as we have seen, for larger amperages, we need larger conductors. The following table is general guide to sizing conductors for feeders and services in single family and dwelling units of 2 or multifamily dwellings. It cannot be used for other services or feeders for other applications. For a commonly installed 200 amp service, the service entrance conductor, the service entrance cable between the meter base and the electrical service panel board with an integral main disconnect will have 2 4-aught aluminum conductors for the hots and a bare 2-aught aluminum grounded or neutral conductor. The following table shows the sizes of service feeder cables, including common sizes for 100 amp, 150 amp, and 200 amp service. And then small conductor size, the 2021 IRC table E3705.3.3 for overcurrent protection rating for small conductors that home inspectors can keep in mind. Looking at the table, we see that a 12 gauge wire copper is minimum size for a 20 amp breaker. The wire gauge is permitted to be bigger than a 12 gauge when connected to a 20 amp breaker. A 10 gauge wire is the minimum for a 30 amp breaker. You can't have a smaller wire, smaller than 10 gauge when it's connected to a 30 amp breaker. All ungrounded branch circuit and feeder conductors must be protected by an overcurrent device. Overcurrent devices consist of circuit breakers or fuses. They are installed at the beginning point of the circuit where the conductors receive their electrical supply. The breakers prevent conductors from carrying current above the determined allowable ampacity. The breaker will automatically open the circuit and protect the conductors if the current is too high and may create a high temperature hazard. For smaller conductors, commonly seen by home inspectors in residential buildings, the rating of the breaker must not exceed the ratings of the conductors. Home inspectors can keep the following table of wire sizes in mind when checking for incorrect wire gauges for certain breakers. AWG stands for American Wire Gauge, which is a standardized wire gauge system. The smaller conductor sizes are normally single-stranded conductors, but as they get bigger, they switch to multi-strand so that they can be easily worked. It is unusual to see a conductor of less than 8 AWG to have multiple strands. A home inspector should look for single-stranded solid aluminum branch circuit wiring, especially in homes built between the mid-60s to the mid-70s. The presence of solid aluminum branch circuit wiring in a home is a major defect. If you observe indications of such wiring and deem it a defect, report it. Let's get this video here going.
The home inspector shall report as in need of correction deficiencies in the integrity of the service entrance conductors, insulation, drip loop, and vertical clearances from grade and roofs, any unused circuit breaker panel openings that were not filled, the presence of solid conductor aluminum branch circuit wiring, any tested receptacle in which power was not present, polarity was incorrect, the cover was not in place, the GFCI devices were not properly installed or didn't operate properly, and other problems related to the electrical receptacles, and the absence of smoke and carbon monoxide detectors.
Okay, we're ready to start the electrical section, which is 3.7 in the SOP. And we're here at the main distribution panel. And I'm going to take a reference photo first with cover on. I'm also going to take a photograph of the indexing that they got here on the inside of the door. And I want to know what the brand name is of this panel as well. So I just took a picture of that so I remember when I sit down and do my report. One thing in this panel is that there are no GFCI breakers or no arc fault breakers in this panel. Now we're going to take off the dead front off the panel. Okay, so now we got the dead front cover off. And typically the way I look at these panels, I'm going to start at the top and move my way down on each side, check for double taps, any kind of damage that might be in the conductors. This is a sub-fed panel, which means that we've got a main that's located remotely somewhere. In this case, it's on the other side of the garage. So coming in here, everything looks pretty good at the top. Now I'm going to look for deox compound on the connections for the lugs, the main lugs. And I can see it. They've all been coated well. So there's no worries there. You see the paste up here? That's our deoxidizing compound. Prevents any oxidation, corrosion of these connection points. Also helps keep the connection points tight. Okay, moving on down here, we do have some double tapping on the ground bar. Over on the neutral side, there are none. Now, typically, double tapping was allowed certain years. So you can note this.
And some manufacturers allow it.
Yeah, some manufacturers allow it because they've got the lugs are designed for double tapping. So now I'm going to come down and just look at my breakers, see if I have any trip breakers. Don't have any. Down at the bottom, I'm looking for missing connectors, damaged conductors of any sorts. Now I'm going to check and make sure my ground is bonded to the enclosure and it is isolated from the neutral. So you don't want to see any jumper wires or any tie bars between the neutral and the ground in a subfed panel. So really this panel looks pretty clean.
I like to point out that the panel is out of date by today's standards because it doesn't have any arc fault or GFCI breakers in it, but there is no requirement to bring it up to today's standards.
Well, that pretty much concludes our interior examination of the main panel. I think we're going to go ahead and put the dead front back on. And always remember your safety part of your inspections. You'll always be very, very careful around this. This is the energized equipment. And keep your clients back from this location at least 10 feet. Okay, now we're going to take a look at the main shutoff for the distribution panel. This particular main is over on the opposite wall from the distribution panel in the garage. We want to do the backhand test right away again. Going to open it up. And we can see that we have one main breaker in here. I also noticed right away that we've got some duct tape over some open breaker holes. So we need breaker fillers in here for safety. We're going to take a photograph of that. We'll take an overall photograph of the main enclosure. So right away, that's the two things I've noticed is the size of the main and the missing breaker enclosures. Now we're going to remove the cover. Okay, we're removing a cover on the main. I'm going to use the same method on this enclosure where the main is as I did on the circuit breaker panel. I'm going to kind of start at the top, work my way down. I want to make sure I've got deoxidizing compound on all of the main lugs. And it looks like I do. Not so important on this bottom one. This is the neutral coming from the meter. This is a copper. So we really don't have to have any deox on that. The other two coming in from the meter, they're both copper as well. So we can get by with no deox. Just checking everything in here is pretty simple. We've got our main feeds coming in here, and then we got the feeders going out to the meter can. The grounding is correct. The grounding should be bonded here to the neutral. And it goes out to the ground rod and to the water main. So everything in here looks pretty good. Okay, here we are at the main service meter. And there's not a lot we can look at inside here. It's got a meter seal on it. And the power company does not like these removed. These are sealed for safety and to make sure that nobody gets in here and modifies anything. So this is pretty easy to inspect. There's not a lot really we can look at. We can check and make sure that it's secure to the wall. I always like to take a reference photo. Want to check our riser. We've got the expandable type riser here, which accommodates any movement in the soil. That way we don't pull any part of our conduit riser out of the fan. So everything looks pretty clean here. We're going to now move inside and start testing some receptacles and some switches and lights. Okay, now we're inside. We're going to test some receptacles and switches. And on this one here in the garage, the first thing I notice is the device cover is gone. I'm going to capture a picture of that and put that in my report. I'm going to test the light. That seems to work fine. We're gonna move down the wall here and we got another device cover missing on the GFCI in the garage. Take a photograph of that, and while I'm here, I'm gonna test. So it did trip when I hit the test button. Now we're gonna reset it. And it came back on. So that part looks okay. I will just say this much about missing device covers. If they're within reach of children, it's very important. It's a huge safety thing to get these covers on there. If they're in another location, perhaps on the ceiling of the garage or some other place where it's out of reach, it's not such a huge deal.
But still pointed out.
It's still pointed out.
One more thing about GFCIs. The manufacturer's recommendation for testing it is to press the test button. And that's the manufacturer's test, but most of us will use the 3-link tester just because that's what we do.
Now let's go ahead and move inside. We're going to test some more receptacles. Okay, so now we're going to start testing some more receptacles and switches inside the house. Before we move on to receptacles, I may want to just mention that in the SOP, it says we need to test a representative amount of receptacles and switches. What that basically means is to test the ones you can get to. That would be advisable, because you're not always going to be able to get to all of them because of bookcases, TV stands, or whatever the case might be. The same goes for windows too. There's a lot of times you're not going to be able to access a window and get it open. I'm going to turn this light on, overhead light, and there's another switch here. It's for the paddle fan. Everything looks good there. So let's go ahead and move on. I use the standard plug-in tester. It's got the 3 lights on the front. It's got the little index at the top. And what I'm looking for is potential reverse polarity, open ground, open neutral. And each one of these has a combination on here. If the 2 lights on the right-hand side come on, that usually indicates it's okay. So we're going to keep moving down the wall. This house is vacant, so we're able to go around to all the walls and test them. This is actually the master bedroom of this home, and there is a master bath attached. So I'm going to just step in there and I'm going to test the GFCIs. There are 2 methods, like Lon said earlier, to test these receptacles. You can either use the plug-in tester or you can use the test button. I'm going to use my tester on this one, and it does work. Do a reset. Retest again, and it looks good. Now I'm going to move to the receptacle down on the other end here of the vanity and see if it trips the receptacle, and it does. But we've got an issue here. I'm showing a reverse polarity when I tried to trip that GFCI. You can see the outer lights are lit up. So we actually have an issue here. I'm going to go ahead and take a photograph of that. I'm going to move back to the GFCI. The GFCI shows it's dead. However, when I test the one that's on this GFCI, it showed that I had a reverse polarity. So obviously we may have some wiring malfunction here. And we're also going to test the lighting and the exhaust fan in the master bath. Everything operated, functioned properly. Now we're going to come out here to the living room area and test a few out here as well. Right here at the base of the stairway railing, we've got a floor receptacle. And in some cases, it may require that you unscrew the cap. And the reason we need one here is because this railing by the stairwell is considered a wall space. So we have to have a receptacle along this wall space. I'm going to go ahead and just test one side. My lights on my tester show it's good. Now I'm going to go ahead and put the cap back on, the cover. These are dust covers. They're supposed to help keep dust and lint and so forth out of the receptacle. Now we're in the kitchen, and we've got all these receptacles here up on the kitchen countertop. And I'm going to go ahead and test all these. And the first one here is a GFCI. Did the manual test with my tester, reset. And that was okay. We've got one here very close to the sink And according to today's code, we have to be within 6 feet, anything within the 6 feet distance from the outer edge of the kitchen sink has to be GFCI protected. Okay, with that, got that one tripped. It appears it's this one over here to the left. And both of these are on that same GFCI. Then if you reset, retest there, and I'm just going to come back over here and do a quick retest here to make sure everything came back on. We're good. When this house was built, the requirement for GFCIs was closer than the 6 feet from the edge of the sink. So therefore, these actually are grandfathered in. We really don't have the authority to make this change or recommend this change. We can recommend it, but we can't enforce it.
But today, everything in a kitchen has to be GFCI protected. But at the time when this house was built, like Ray says, this is good. We move on.
We've got a island countertop here, and according to the code, at the time this house was built, there should have been a receptacle on each end of this countertop, but right now there's just one. So we would have to put this in our report that the opposite end of that receptacle, there is none, and we're going to recommend that they're have an electrician put one in on this end as well.
The reason we do that is kitchen appliances only have a 3-foot cord. And so we can't plug in an appliance on this end of the island without using an extension cord. And we don't like extension cords.
Okay, we've gone through, we've tested all the lights, the receptacles. We've taken a look at the circuit breaker panel, the circuit main. We're now going to conclude our electrical section, which is 3.7 in the SOP.
All right, team, let me get back over to my other screen. Oh, there we go. And back to PowerPoint. All right, we're back. Let's go to the next slide. All right. Most important though, stay safe, guys. And gals. But the most important concept in this course is safe. Stay safe. Compared to inspecting a roof from an area, above the ground, the electrical portion of a home inspection is arguably the most dangerous. Many things can go wrong in an instant, and some mistakes can be fatal. That's why home inspectors should understand safety procedures, including what causes electrical shocks and arc flashes, so that they can avoid hazardous situations while inspecting. Safety is the most important aspect of performing an electrical inspection. Can you guys hear me okay? All right, good deal. Thank you. All right, standards of practice. Some inspectors may choose to go beyond the standards of practice because they suspect some sort of defect and want to provide fuller information in their reports for their clients. Inspect to your capabilities and safely. So. And all right, now we're starting to get into the stuff, getting out of the concepts and getting out of theories and stuff, and we're getting more into the information that we can readily use in an inspection. So starting with working space and clearances, adequate space should be provided around the electrical panel board for safe access to the components. Generally, the working space in front of the panel board must be at least 36 inches. The working space on the sides is 30 inches. I'm sorry, front of the panel board is 36, to the sides is 30, and at least 6.5 feet in height. Panel boards must not be located in bathrooms, toilet rooms, closed closets, or over the steps of a stairway. Overcurrent devices must be readily accessible. We're going to have some awesome pictures of stuff, that where we don't see this kind of thing. And obviously, stating that panel boards must not be located in bathrooms, toilet rooms, closed closets, or over steps of stairways. We all know that in older homes, we see that stuff a lot. And what we do, or what I do, is just, recommend an electrician to upgrade at the convenience of the buyer. Because it probably was okay whenever it was originally installed. I mean, sometimes not, but whose responsibility is that really? So each circuit should be distinguishable from all the others. Spare circuits should be labeled accordingly. There should be a circuit directory installed on the face of the panel board door, inside the panel door, and the location adjacent to the panel door. The circuit labeling should be permanent and legible. Homeowners and contractors could use factory-made panel labeling kits. The requirement helps protect occupants and contractors from injury that could result from shutting off or turning off the wrong circuit breakers. Home inspectors may often find that panel board door with illegible markings, misspellings, or multiple duplicates. And we should recommend those to be updated. If the markings at the breakers of the panel board are not legible, a code violation exists, and that condition is a defect that needs correction. Potential hazard exists where circuit breakers are mislabeled or ambiguously labeled because the occupants or electrical workers might not be actually turning off what they intend to turn off. Because this is a safety issue, panel directories must be labeled plainly with words that provide complete and accurate descriptions of the circuits served by each overcurrent device. Basics of AC current. Everyone should understand that it's possible to receive an electrical shock whenever electrical power is present, regardless of the level of power or presence of any protective devices. Most 120 volt circuits are wired to deliver 15 or 20 amp circuits. Some devices can hold an electrical charge even after the power has been turned off, especially items that have a motor in them, refrigerators, dryers, anything like that. So be especially careful when you're testing and looking at those types of devices. There are warning signs that a panel board, cabinet, or box or the system in general may be compromised, and these should indicate to the inspector to defer further evaluation to a licensed electrical contractor. All right, knockouts on a panel board range in size from 1/2 inch to 2.5 inches in a typical residential construction and are referred to in trade jargon as knockouts because a plug has to be knocked out with a tool to create an opening where a box or enclosure has been factory pre-punched. Knockouts being left open and unused in boxes and other cabinets is a very common problem. A knockout opening in a box is sometimes covered with tape, which is not equivalent to the wall of the box, and that is a defect. Unused openings must be closed with appropriate materials for the protection of the circuit conductors and devices, as well as for protection against shock by someone inserting a finger or a tool into the enclosure, usually kids. Listed knockout plugs are available for this purpose. Metal plugs used with non-metallic boxes will not be grounded, and recessing them 1/4 inch from the outer surface will limit contact. The idea is to help prevent inadvertent contact with an energized surface. This section is not intended to be applicable to holes provided for fasteners for mounting purposes, cooling slots, and similar openings that are a part of the design of the listed equipment. In the context of this section, unused openings are openings that are drilled, punched out, or knocked out of the enclosure. What is an arc flash? An arc flash occurs when a flashover of electric current leaves its intended path and travels through the air from one conductor to another, or neutral, or to ground. It often happens unexpectedly and can be explosive but brief, or it can last seconds and be rather visually spectacular. It can cause a little damage, or it can disable a system and require the replacement of the equipment. An arc flash of any size is quite dangerous because its path is unpredictable. It will be attracted to the nearest item with the greatest conductivity, such as an unsuspecting rodent, house, pet, or a person. An arc flash can cause a serious electrical burn or even fatal electrocution. How serious is an arc flash? All three factors that will determine the severity of an injury caused by an arc flash are proximity, temperature, and the time it takes to break the circuit. An injury due to an arc flash can be quite serious because of the violent nature of such a powerful burst of electrical energy. You guys can keep reading this, but a real quick example is I had a class that was being conducted by the Arkansas College electricity owner, and he had an arc flash incident on a residential electrical subpanel, and he was blinded for about 3 days. He was not wearing a face shield. You know, he was an electrician and just doing what a normal electrician does, and that arc flash occurred. And so, like I said, he was blinded for 3 days, and when he explained it to me, he said it was like in the space between you and the panel, it's like a VW bus is magically put in front of you. That's the amount of force and power that occurs from an arc flash. So, gentlemen and ladies, be very, very careful. Some inspectors have been blinded permanently. Definitely severe burns. And I guess one of the other major issues is that plasma ball that occurs from an arc flash. If you are all of a sudden surprised and you breathe in really quick, you can intake some of that plasma, and it will go into your lungs and cause you lung damage. So, like I said, it would be highly advisable to use the proper PPE when you're opening an electrical panel. All right. Assess your risk tolerance. You are not required to perform an invasive electrical inspection. Removing the dead front of an electrical panel board exceeds InterNACHI standards of practice. Wear PPE, regardless of whether you choose to exceed the standards of practice or not. Always wear the appropriate PPE. Check your surroundings. Look for identifiers that might be indicating that there is a problem with your with the electrical system. Using the appropriate tools, making sure you're not sticking an all metal screwdriver inside of a panel, all that good stuff. And then always make sure you protect your clients. I think you always have that super curious client who you have a panel cover off, and they go in and they, what's that? And they put their finger inside the panel. You always want to tell your clients that if they do happen to be following you around, that they need to stay at least 5 feet back from you while you're doing that, because the opportunity for arc flash is significant. Arc flashes are just one of the more serious examples of what can go wrong during inspection, which is why inspectors should follow their training as well as their instincts and protect themselves and their clients on the job. It's always better to be safe than sorry and incur a grievous injury, which can put both you and your life at risk. All right. Yeah, there we go. Service entrance conductors. Here we go. All right, the service entrance SE cable, the blue arrow, is a line of let's see. The blue arrow is a line of service conductors. The white arrow is located between the terminals of the service equipment to the main disconnect, and they point usually outside the building, clear of building walls, where they are joined by tape or splice, the orange arrows, to the service drop or the overhead service conductors, which is the red arrows. The service equipment is the necessary equipment, usually consisting of a circuit breaker or switches and fuses and their accessories, connected to the load end of the service conductors to a building or designated area, and intended to constitute the main control and cutoff of the supply. It is understood that raceways, fittings, and enclosures housing service conductors are also part of the service equipment. Meter socket enclosures are not considered service equipment. Meter enclosures do not have interrupted ratings, disconnecting means, or overcurrent protection. The red arrows point to the service drop, which is the IRC section E3501.1, are defined as the overhead service conductors between the utility electric supply and the service point, which are the orange arrows. The white arrows are also service conductors. They are referred to as overhead service entrance conductors. They are the service conductors between the terminals of the service equipment and a point usually outside of the building. Clear building walls were joined by a tap or a splice, which are the orange arrows, to the service drop or the overhead service conductors. The important commonly used term for home inspectors are overhead service conductor, red arrows, and the service entrance conductors, which are the white and blue arrows, and the splice, which are the orange arrows. The SE and SE cable stand. Oh, I'm sorry, gentlemen, and folks. I figure we're gonna go for 50 minutes. We're at 50 minutes right now. We'll take a 10-minute break. So if you guys would come back here at let's see, what time is it right now? Right at 4 or 5, in 10 minutes, whatever your time is, because we're all over the country right now. So 10-minute break. So in the Q&A, our top one from Jeffrey: should the GFCI trip the light in the bathroom as well as the outlet? No, that is not required. Down here, I recall New York requires the panel board cover being removed. More than likely. And I know in Arkansas, which is where I am, we do require that the panel board cover be removed. That was for, oh, Scott already answered that question. All right. See a lot of, from Paul, see a lot of panels in finished basements behind doors and cabinets. What is the rule for access to those? Just, it's 36 inches to the front, 30 inches on the sides, and it cannot be in a wet location. Now, obviously, a lot of homes, that was deemed okay back when they were originally installed, or there wasn't, a code requirement, or there wasn't code enforcement. So anytime you see anything that is within those locations, I would just recommend them to be upgraded, not necessarily repaired or replaced. That's, this is my opinion. I would just recommend them to be upgraded, and whoever wants to do that, or however they want to negotiate that, that's up to them. All right. Mr. Condover, is the 6-throw rule still applicable? Yes. That rule still is applicable. We will go through that later in this course. Please discuss finding and documenting the external ground wire and vessel not always visible due to included the external wire. So I think I was somebody else asked this question and I typed it to them, but yeah, so if you don't see, and we're going to go through this also, but if you don't see an external ground wire, there must be some type of grounding on the home. So usually that means you're going to find a UFER ground somewhere on an exterior wall in the garage or in the home, and it really should be as close to the exterior electrical disconnect panel, meter, whatever, should be on the opposite side of that wall. So if you can't find an external grounding conductor, ground wire, or grounding rod, then look throughout the house for a double blank wall plate, which will usually hold your UFER ground. And we'll go over what a UFER ground is later if you're not sure. Daniel, what is the main cause of an arc flash when removing a dead front? So it's the wire. So you could have a loose wire. So basically, anytime you have an electrode, and let's see, we still got 5 minutes here. So anytime you have an electrode and a supply, if there is any type of a gap between those two, you have the potential for an arc. Now, an arc flash is just a more so when you get that sparking or that igniting, that's an arc. So it's just if you have if you happen to have a dryer that is pulling a lot of power and it has that loose connection there, if the electrode gets far enough away from that breaker, maybe they're let's say nut or the screw is not tightened down, the lug, there's what I'm looking for. The lug is not tightened down and it's pulling away from there. If it gets far enough away and that dryer is pulling power, you could have a very large arc flash, so you have loose wires, or you could have a screw penetrating through a wire. If you're backing that screw out of that panel cover, the panel board cover, that'll create an arc flash. So a lot, it's anywhere where you have the item, whatever's have power on it, and whatever any electrode or any other metal device or anything that's close to that, you could have an arc there. Never heard of the railing is considered a wall space and therefore a receptacle before is needed. Where is that in NEC? That one I will have to do some research on. So I'll get back to you on that one, Christopher. Let me write that one down. So handrail outlets. Please discuss the changes to the main service panel when a generator is added to include bonding. So generators are outside of our scope. So we really, if there is a generator, anywhere in the system, I automatically refer that out to a licensed electrician. So, for purposes of this class, we're not going to cover any generator items, but ideally, if a generator is on the system, the generator component, you might have, a breaker that is inside of a panel that is specifically for the generator, but the generator components should be separate from the system. So I would say, we won't go over anything concerning generators in this class. Should I expect, let's see, from Eric Foster, should I expect circuit problems related to my panel board having a defect and therefore make a reference in my report with recommendation for further evaluation? If you expect any problems, if you see any melting of the wires, if you see any black marks inside the panel, let's see what else, any type of, if the panel doesn't look perfect, I would recommend an electrician. Because when it comes to electricity, one defect can cause a fire. So I always want to be safe, cover your bases, and if you see any evidence of damage or things not seating correctly, or I've seen where they've tried to shove a breaker into one type of breaker into a different type of panel, and the breaker is not seated correctly. Always recommend. Excuse me. Sorry about this. 1 second. Yeah, if it's not perfect, recommend an electrician. Any chance you have questions answered while we're not on break? Well, we have 50 slides to go through in 50 minutes, so that's a slide a minute, and we still have videos and other things. So if you have any questions that we don't cover, please feel free to email us, email Kayla. You can email me at admin@tradexuniversity.org, and I will find your answers. The handrail outlet question, I will definitely find an answer to that, and we'll let you know. Folks, we're going to go back to the webinar, and we'll hit some more questions in the next break. All right. So back to service entrance conductor cable type. So in the SE cable stands for service entrance. This cable assembly is designed with a high degree of resistance to mechanical damage and the sun's UV ultraviolet rays. For this reason, it is not installed in a conduit, but is attached directly to the building. If it is located someplace where it's likely to be subject to physical damage from car doors or whatever else, weed eaters, that type of stuff, it needs to be identified and recommended for upgrade for additional protection. SE cables should still feature gooseneck or service head cap, and the end where the individual conductors exit the sheathing should be protected from moisture intrusion by a heat shrunk sock if a gooseneck is used. Basically looks like somebody took like a rubber wrap, or saran wrap, which is just really thick saran wrap, and wrapped it all up and then heated up with a heat gun so that it forms a seal between the wire and the entrance. This cable should typically be attached to the building every 30 inches along its length and within a foot of its top and any meter can. So basically, you just don't want it hanging loose off the wall, like some of these are here. All right. SCU is an unarmored service electrical 3-wire cable with 2 conductors and a neutral. The SCU typically has a stranded neutral conductor that wraps around the cable to create an oval shape. SCU cable has a neutral conductor but does not have a grounding conductor. Since neutral conductors and grounding conductors are connected at the point of service disconnect, SCU cables can only be used up to the service disconnect to avoid significant safety concerns. SER is a round service electrical 4-wire cable that typically has up to 4 conductors and a bare neutral. The cable is designed to be used in feeder panels and branch circuits. SER cables are equipped with neutral and grounding conductors, which make them perfect for use after the service disconnect. The image shown shows a 200 amp panel board supplied by a 4-wire SER, where the main service disconnect is installed as the meter outside, or at the meter outside, and the additional disconnect is installed at the panel board. Service entrance conductors, like all others, are made from either copper or aluminum. Aluminum conductors need to be sized larger than copper ones for any given amperage. Aluminum terminations may also be coated with an antioxidant to prevent corrosion, although the more recent AA8000 aluminum alloy conductors do not require it. The manufacturer may or may not recommend antioxidants. The typical electrical service for homes in North America is 120, 240 volt split phase systems provided by a pole mounted distribution transformer located at the service drop, which is made up of 2 120 volt lines and a neutral line. This triplex cable may include a messenger cable located at the middle of the neutral conductor that provides support over long spans. The neutral line from the pole is connected to an earth ground near the service panel, which is usually a conductive rod driven into the earth. The service drop provides the home with 2 120 volt lines of opposite phase, so 240 volts can be obtained by connecting a load between the 2 120 volt conductors, while 120 volt loads are connected between either of the 220 volt lines and the neutral line. The 240 volt circuit is used for a home's electrical appliances that require substantial power, such as a furnace, water heater, air conditioner, washer and dryer, and oven or slash wrench. The 120 volt circuit is used for lighter electrical loads, such as household lighting and portable appliances and electronics that are plugged into the home's standard 2 or 3 prong with a ground wire, electrical receptacles or outlets. Whether it arrives overhead or underground, a neutral conductor originates as a center tap of as the neutral conductor originates as a center tap of the secondary winding of the utility transformer that supplies power to a 3-wire, single-phase 120-240 volt system. The 2 ends of the secondary wiring are the ungrounded conductors, and the midpoint of that winding is the neutral point from which the neutral conductor originates. See the illustration below, or to the side, with the 2021 IRC. The neutral conductor serves as the common return conductor for the 2 ungrounded conductors. The neutral conductor is always a grounded conductor, but a grounded conductor is not always a neutral conductor. Definitely sounds confusing, but the only grounded conductor is the neutral conductor. Most people refer to all grounded or the white conductors in branch circuit in a dwelling as neutral conductors, because they all connect to the grounded neutral conductor in the service, although the code refers to them as grounded conductors. All right, that was a lot. Homes in European countries use three-phase power, having longer service drops that can serve multiple residences, which is an economical approach to providing power to dense populations in small areas. This type of service drop consists of three-phase wires and one grounded neutral wire. All right, electrical service is a general term used to refer to all electrical conductors and equipment. The service begins at the load end of the service drop or lateral and ends at the panel board cabinet that houses the main disconnecting mains. Power from the utility company is typically delivered through three large conductors, which may enter the house overhead or underground. Overhead service wires are called the service drop. The service drop runs to a weatherhead at the top of the length of the rigid conduit called the service mast. Refer to the following illustration for the primary components and measurements as the service mast above the roof surface. The service point is the point of the connection between the facilities of the service utility and the wiring at the house. The point of attachment of the overhead service conductors to a building or other structure should be not less than 10 feet above the finished grade. These are great diagrams. I was giving everybody a chance to look at them. So next. All right, when the service drop is located above the eaves, the service mast or riser is run through the eaves. When run underground from the utility pole to the electric meter, service conductors are installed in a buried conduit or run as the underground service entrance cable. The illustration shows the main components of a common underground service installation, including the meter, main service panel board, and the grounding electrode conductor. All right, the main service grounded conductor, which is the neutral, connects to the neutral bus bar. The location of the neutral bus bar varies depending on the panel manufacturer. It is a silver-colored bar with many holes and screws and one larger hole for the main service grounded, which is the neutral wire, or which is the neutral of that wire. There are, however, a few variations of this thing. It is not unusual to see one of the live conductors tied back. This is indicative of a 120-volt supply only, which is installed in some older properties, apartments, and condos. Conversely, the inspector may see cable assemblies with more than three connected conductors. This is typically a three-phase supply commonly found in both commercial, agricultural, or multi-family dwelling units. In the case of 120-volt supply only, we recommend that the inspector's report shows the limitation. In the case of the high voltage three-phase supply, we recommend the inspector defers this part of the electrical inspection to a qualified industrial or commercial electrical contractor. Let's see, the point of attachment to the building or the structure. A typical three-wire service drop consists of two insulated hot conductors wrapped around a bare stranded aluminum wire with internal steel messenger cable. The bare aluminum wire also serves as the neutral. The inspection image shows the overhead service drop and weatherhead, including two hots, one bare to the two hots and the one bare stranded service neutral. The neutral grounded conductor also serves as the main physical connection through though insulated to the building. The inspector should ensure that this strain relief is not detached or pulling away from the structure. You'll often see that in around houses that have a lot of trees, and if you have a storm and a tree branch or a tree falls on the wires, and that can pull the connection away from the home. So pay close attention to that stuff. The point of attachment of the service drop conductors to a building or structure must have a clearance above finished grade of at least 10 feet. Obviously, that's for safety. You don't want anybody reaching up and grabbing any wires or vehicle potentially driving into the wires. Here's some great examples of that. The overhead service must have minimum separation from both the structure itself and any walkways, driveways, balconies, patios, and swimming pools. Often, an inspector will see properties that have been modified and the service overhead should have been relocated, but it wasn't. Very common with decks. This can obviously lead to some dangerous conditions, especially over swimming pools and decks where the service connections could be accidentally reached by a home. Here's a good example or good diagrams of the clearance recommendations or requirements for distances. And if you need to, you can always refer to the code reference down there on the bottom right. E3604.2. Conductors must have a vertical clearance of at least 8 feet above the roof surface with a distance of at least 3 feet in all directions from the roof edge. There is an exception though, excuse me, for low sloped roofs or flat roofs with a surface accessible to pedestrians, such as a balcony or deck. Overhead service conductors supported on and cabled together with a grounded bare messenger wire above a roof surface subject to pedestrian traffic must have a vertical clearance from the roof surface of at least 10 feet. The minimum vertical clearance must be at least 10 feet at the electrical service entrance to the building at the lowest point of the drip loop of the building and building electrical entrance and above areas or sidewalks accessible by pedestrians only. Such clearance shall be measured from the final grade or other accessible surfaces such as a deck or balcony surface. If it's just a flat roof with no pedestrian access, then the clearance is 8 feet. Blurry pictures, and we're going to have a few blurry pictures through here. I apologize. I'll be updating these slides in the future with a lot clearer pictures. But you can kind of see in this picture where the tree has pushed the wires out. So another common clearance problem is caused by trees and shrubs. Inspectors should take time to eyeball the length of the supply from the pole to the attachment on the structure and report any tree limbs touching the conductors. Also, remember that branches are heavier during the summer, and way down further on the conductors. What may be marginal during the winter months may well cause a problem later in the growing season. This also applies to obviously snow-laden trees too. The inspector should recommend that any limbs within 5 to 6 feet of the cable assembly be cut back. In most cases where the home is fed by a service overhead, the supply is fed down the outside of the house through a conduit known as the service mast. In some cases, the cable assembly is of type SE, which requires no conduit. The masthead, or gooseneck, as it sometimes is called, is the top of the mast itself. Its purpose is twofold: to act as a rain cap to stop moisture from entering the conduit, and to provide bushings to prevent the individual conductors from being damaged by rubbing against the metal components. In an electrical power situation, a bushing is an insulated device that allows an electrical conductor to pass through something else that may be conductive. The masthead should be undamaged and securely fastened to the service mast. The inspector should report any loose fittings or cracks in the masthead and its clamp. In the middle top picture provided by Brian Goodman, the service has been damaged by a falling tree branch, and not only was the masthead smashed, but also the neutral conductor splice was torn apart and repaired using jumper cables from a car. The drip loop: before the conductors enter the service mast, there should be a loop in the conductors. The lowest point of these loops should be 12 inches below the point of entry into the masthead itself. This is to prevent rainwater from migrating along the conductors or the cable assembly and pouring down into the masthead. In the middle bottom image provided by David Mackey, it is clear that there is no loop in the conductors. In this case, it's caused by failure of the cable assembly connection to the home. Service masts. Service masts for supporting the service drop and overhead service conductors should be of adequate strength or be supported by braces or guide wires. A mast in excess of 3 feet above the roof surface may require support. The weight of the cable assembly is considerable, and when applied to an overly tall mast, has the ability to bend it over. For the same reason, the inspector should report anything other than the cable assembly being supported by the service mast. The inspection to the left shows a tall mast that lacks adequate support. It is common to see telephone cables, TV cables, satellite dishes, clotheslines, and supply to remote buildings being supported by the service mast. The overhead service mast must not support such things as cable TV and telephone wires. The inspector should report all of these as in need of repair or correction. The IRC is silent on the size requirement and conduit type to be used for the mast for the riser. It is also silent about the height above the roof it can extend before being supported by braces or guide wires. In many jurisdictions, the power utility company specifies these requirements. As with any other projection through the roof surface, the service mast should be adequately flashed to prevent water from entering the building. In the case of the rigid conduit service masts, they should be attached to the structure every 5 to 6 feet throughout their length and should also have a clamp within 12 inches of either side of the meter base, as well as the top of the mast if it doesn't project through the roof. The underground service conductors between the electric utility supply system and the service point is called the service lateral. If the utility company has an underground supply system with transformers on pads at or near the property line, the service lateral is that which runs underground to the house from the transformer installed on the ground. If the electric service is overhead, the homeowner may not want a service drop or overhead line run across the property. In such cases, the conductors can be run down a utility pole in a raceway and then run underground to the house. Both of these installations would be called a service lateral, which is defined by the IRC in Chapter 35 of the 2021 IRC as the conductors from the utility main line to the point at which they connect to the service equipment or service entrance conductors at the house. The service lateral typically terminates at a meter or main disconnect enclosure. The underground service conductors, the service lateral, is an underground system for the service entrance conductors. For underground service, the service entrance conductors connect to the service lateral and run to the terminals of the service equipment, which is likely the main service disconnect. Direct buried cable. Type UF cable is rated for direct burial and has an outer sheathing that is resistant to moisture and damage from the soil. This type of cable must be buried to a depth of 18 to 24 inches. And if embedded in rocky ground, must be installed in a manner that will not damage the cable. This cable still needs to rise in a conduit to prevent mechanical damage before it enters the building. The visible underground conduit should be made of either galvanized steel or gray plastic rated for this purpose. Some of the three main issues with underground cable, UF cable coming up out of the ground are lawnmowers, weed eaters, and dogs. Where the service entrance cable is not rated for direct burial, it needs to be in a full conduit and must be buried at a minimum depth of 18 inches under landscape and 24 inches under hardscape, such as driveways. Where the service conductors are buried underground, they are required to have a ribbon embedded 12 inches above the conductor unless they are under the exclusive control of the utility company. The home inspector should evaluate any visible above ground conduits and report any damage or open joints that would allow moisture into the assembly. Oftentimes, well, not oftentimes, but sometimes, if you have an overhead service that is going down into a conduit that is going underground to the house, during a rainstorm, if that conduit is not sealed and have goosenecks or weather masks on them, you'll see water pouring out of that conduit at the house, especially if the power pole is up on a hill and the house is down lower. So keep an eye out for indications of water overflowing a conduit or moisture staining around an electrical conduit. The electric meter is not considered part of the service entrance equipment. It is there to measure the amount of power used on the property. Some properties may have more than one meter, maybe due to multiple occupancy or discounted power for heating use. Meter bases can be configured with a panel board location in several ways, as shown in the illustration. The main disconnect can be installed at either the meter base or the breaker panel. As the meter is a rated component like any other, the ampacity of the meter and its base cannot be lower than the stated total allowed available amperage. As meters have increased in capacity over the years, the meter bases have changed. The very earliest meters, such as the inspection image shown, had no separate base and were typically rated for only a 30 amp supply. Understanding meter bases is an important part of being able to properly evaluate the maximum available amperage in the home, but should not be relied on completely when sizing a service. A good example of this, I unfortunately had to go through in my company, was we had a square meter base on the outside, which indicated 150 amp service. And but then on the inside, we had a 200 amp disconnect. And unfortunately, one of my inspectors happened to miss that. And the homeowner or the buyer who ended up buying the home asked for an electrician to come out and install electrical circuit for electric dryer. And that's when it was found that we happened to miss that. So keep a special eye on your meter base on the outside and what your panel and your main means of disconnect is if it happens to be on the inside. It was a remodeled home, so at that time they didn't require an exterior disconnect. So just keep an eye on that stuff. Different types of meters. So you can see the round meters on the left are typically 60 amp meters. In the middle, you have the square meter base, which is the 100 amp service. And then your modern, which is your rectangular, had a 200 amp rectangular base. Here's some more. You have combos. A lot of times, especially on remodels, you have combos of different types of panel sizes, panel covers, and meter bases. And then on, especially on your larger homes on the right-hand side, you have a lot of times you have 400 amps of disconnect, or 400 amps total of service to the house was divided into two 200 amp services. All right, generally speaking, the difference between grounding and bonding. Grounding is a direct connection to the earth to aid in removing damaging transient overvoltages due to lightning. Bonding ensures the electrical continuity of a fault current path to provide the capacity and ability to conduct safely any fault current likely to be imposed and to aid in the operation of overcurrent protection device. Properly bonding all metal parts within an electrical system helps ensure a low impedance fault current path. Ensure a low impedance fault current path. The issue of grounding and bonding confuses many inspectors. Due to its complexity in this section, we will try to break down to its fundamentals and look at the basic requirements and common failures that can lead to unsafe conditions around the home. Grounding. So starting at the beginning of the electrical service, the last stop on the utilities distribution chain before the supply goes to the building is the transformer. Refer to the illustration to see the location of the transformer. This steps the high voltage primary distribution down to the neighborhood to the 240, 120 volt feeds the home needs. The transformer has a winding known as a phase coil that is center tapped to provide voltage stabilization and a return path for the higher voltage systems to aid in clearing primary side faults. On a typical 240, 120 volt for service drop, we will have two ungrounded conductors and a single grounded conductor. This means that we have established our own grounding electrode system at the house. Look at the illustration and check the three grounding electrode conductors coming from the main panel. One connects to the metal water pipe, another connects to the driven ground rod, and the third connects to a copper wire inside the concrete. This is critical for removing dangerous voltages imposed on the system via lightning strikes and overvoltage surges from higher voltages on power lines. If a grounding rod, pipe, or plate electrodes are used, they must have a rating of 25 ohms or less. Otherwise, an additional electrode must be added per the NEC. The grounding rod, footing reinforced steel, and metal underground water pipes are examples of grounding electrodes, which are metal electrically conductive terminals through which current enters the earth. There are several methods of connecting the grounding system to the ground, with a driven grounding rod being the most common in most areas. Most residential construction requires two separate grounding electrodes in combination of the following, which need to be at least 6 feet apart. Driven rods, which are the rod type grounding electrode, metal water pipes, well casings, UFR grounds, ground plates, steel framing, and ground rings. Historically, the grounding system had just one connection to ground, and this was nearly always made on the water supply pipe. However, two connections are now required by most jurisdictions to ensure a low impedance ground. Because most utility companies now install plastic potable water supply lines, a water pipe cannot be used as a grounding means. So one of the other electrodes listed must be used. It is also important to note that all electrodes are present in the dwelling must be bonded together to form a single and complete grounding electrode system. Typically, the two required grounding electrodes need to be at least 6 feet apart. If one is the water pipe ground and the supplemental is a ground rod, another ground rod may be added in order to meet the requirements of the NEC. Gas piping should not be used as grounding electrode for safety reasons, but in most areas, gas lines are required to be bonded to the grounding system if they're likely to become energized. Quick note on that. In the National Plumbing Code, it is required to ground the black gas distribution pipe if, we're going to go over this in a little bit, if CSST, the yellow CSST, is connected on the system. Now they have, I think that's later in this course, but now they have a arc resistant CSST, which has a black sleeve over it, which bonds the connections, the nuts on the ends, and it bonds the system to the black pipe, which also maintains continuity to the device that the gas pipe is hooked into. So it's going to be like your furnace or your water. Rods made of stainless steel and copper or zinc coated steel shall be at least 5/8 inch in diameter. Grounding electrodes of pipe and conduit must be at least 3/4 inch. There are special listed rods, and listed rods may not be less than a 1/2 inch in diameter. If pipe or conduit is used as a grounding electrode, it must also be no less than 8 feet in length and no smaller than 3/4 inch. If a micrometer or similar device is not available, the home inspector shouldn't guess the rod's diameter. If visible, you may be able to confirm the diameter by looking at the listed markings, which may indicate that the rod complies with the diameter requirements of the NEC. The listing agencies and like UL will mark rods that are greater than 1/2 inch in diameter and that will have the correct minimum amount of total. Rod and pipe electrodes must be at least 8 feet in length to be considered a grounding electrode. All rods should be driven 8 feet into the earth. The rod and pipe electrodes must be installed at least 8 feet of length in direct contact with the soil in the ground. They must be driven into the ground at least 8 feet. They could be driven at an angle, but the angle should not be more than 45 degrees off vertical, or the rod could be buried in a trench that is at least 30 inches deep. Sometimes in very rocky earth, the rods cannot be driven perpendicular to the ground, so they may be driven at an angle of less than 45 degrees. If they cannot be driven at all due to unfavorable soil conditions, they can be installed in a trench no less than 30 inches deep. But no part of the grounding electrode can be closer than 6 feet to any other. The upper end of the electrode should be flush with the ground or just below the ground surface so that the end and attachment are protected from damage. Oftentimes, we will not see that. They will be above ground and sometimes well above ground so that weed eaters, which is probably the most common, and animals will damage them. If you find a rod sticking out of the ground, that's a defect. It should be at or just below the soil surface. Pipe or conduit made of steel shall have an outer surface that is galvanized or otherwise metal coated to resist corrosion. If the material is iron or steel, the electrode must have its outer surface galvanized or metal coated for corrosion protection. The ground wire, the grounding electrode conductor, needs to be fastened or attached with the correct approved clamp, and the attachment needs to be rated for direct burial if located below ground. It is common to see the acorn clamps installed improperly, where the conductor clamped under the screw rather than under the solid part of the clamp, which has the biggest contact area. You can see that in the left diagram. Connecting to the main metal water pipe in a house was the most common type of connection at one time. The image on the right shows cast iron or cast bronze clamps for connecting a wire to the water pipe. Where the metal pipe is used as a grounding electrode, the conductor should be connected with clamps rated for water tubing and needs to be connected within the first 5 feet of piping as it enters the structure. Since the water meter is a removable part of this potential circuit, a jumper cable needs to connect the pipework on either side of the meter to ensure continuity at all times. Let's see, you can see a jumper or a bonding conductor is a conductor used to ensure that there is electrical conductivity between metal parts that are required to be electrically connected. For example, a jumper may be installed over the water meter because the continuity of the ground path or bonding connection of the interior pipes should not rely on the water meter. The jumper is a large gauge conductor that jumps over the water meter and is securely attached to the metal water pipe on each side. And then not shown are well casings. As wells are bored to a great depth and lined with metal sleeves, they make good grounding electrodes as long as they are far enough away from other grounds and are properly connected. With so many homes and commercial buildings now built on concrete, steel reinforced slabs, this grounding system has become very common. Talking about UFA grounds. The requirements for UFA grounds are that they have either 20 feet of number 4 rebar or 4 AWG copper wire embedded in at least 2 inches of solid concrete within the footer that is in contact with the earth. This system must also have external means of connecting other grounded systems to it, such as telephone wires. So a lot of times you'll see the a lug connection on the outside of the meter box on the outside. If you don't see a ground on the outside of on the outside of the home on the exterior means of disconnect or the meter, oftentimes you'll see different lugs or a bus bar that's connected there, or they actually have a device now that comes out of the bottom of the panel that has your green grounding screws on that you can attach into that. The rebar, the rebar is painted green, so its presence can be verified by the local NHJ, just to make sure that everything is correctly identified. Sometimes you'll have ground plates. In some cases, ground plates are used as the grounding system, but it's very uncommon. In residential, ground plates are made of ferrous metal, shall have a thickness of no more or no less than 1/4 inch. Steel framing. You see this in steel, outbuildings, barn dominiums, that type of stuff. And then ground rings. Although it's very rare in residential construction, a ground ring may be installed where a minimum 2 AWG conductor is buried to a depth of at least 30 inches right around the structure. The GEC can be copper, aluminum, or copper-clad aluminum. It is not intended to carry current except in the case of a ground fault. It can be bare and without color. Its size is related to the amperage of the surface entrance conductors. The table below, or table to the left, or I'm sorry, I'm looking to my left. The table in the middle shows the sizes of the GECs. Remember, the GEC should be connected only to the neutral at the service panel, the panel containing the service disconnect, and nowhere else. We are constantly fighting with our, or not, I would say not fighting, but conversing with our local electricians as to where where this occurs. So in our area, we have a lot of panels or a lot of main disconnects that are in the yard, at the meter, at the back of the house, and the easement. That is considered, if there isn't a disconnect there, that is considered the first means of disconnect. And everywhere else past that should have the neutral and the ground separated or isolated. The GEC is usually connected to the ground service conductor in the service equipment where the main disconnect is located or in the meter enclosure. The grounding electrode conductor is the grounded service conductor and the grounded service conductor are bonded together to the metal service enclosure by the main bonding jumper, screw or jumper connecting the neutral bus bar to the cabinet enclosure. The equipment grounding conductors or the grounding wires are also brought to this point and tied to the grounded service conductor, to the neutral conductor, and to the grounding electrode conductor, which is the GEC. The other end of the grounding electrode conductor is connected to one or more grounding electrodes, such as the grounding water pipe and the ground rod. Rod and pipe electrodes must be at least 8 feet in length to be considered a grounding electrode. The rod and pipe electrodes must be installed at least 8 feet of length in direct contact with the soil in the ground. No part of any grounding electrode can be closer than 6 feet to any level. And we've talked about this. Surge protecting. This is coming very, very common. This is required by our AHJ in our area now. So it may or may not be required in your new construction in your area. But whole house surge protectors should be installed on new panel boards. A surge protector protects the home circuits in the event of a power surge through service conductors, such as a lightning strike or power surge. These devices are typically connected through a dedicated 240 volt breaker. They cannot be double tapped into a existing 240 volt breaker. You see that a lot. There is usually an indicator LED light that indicates the proper function of the surge protector, which is why we had a rash of electricians that were installing them behind the dead front. So you cannot, that defeats the purpose and you cannot see the indicator lights. So if you see, one of these devices behind the dead front, recommend that it be brought out to outside the panel. And I would, on the front of that surge protector, it'll tell you what the lights mean. Every manufacturer has a little bit different. It could mean if they're green, they're good. If they're red, they're bad. If they're not lit up, that could be bad, or that could be good. So just read, the instructions that are on the unit itself. Or if they don't have instructions, you can always try and find the model number and look up the instructions online. As the main service panel board that has the initial main disconnect, neutral conductors, which are the white wires, equipment grounding conductors, which are the bare copper or the green insulated wires, and the metal service panel board cabinet, and the grounding electrode system, which are the ground rods, must all be bonded together. Excuse me. Code requires that the grounds and the neutrals be kept separate except at the main disconnect, which is the first disconnect after the meter. If the electric service system has its primary main breaker outside at the meter base, the neutral and the ground would be bonded only at that point, not at the breaker panel. When the main disconnect is located at the meter base, the ground and the neutral terminal bars must be separate and not connected, and the main bonding jumper must be removed or disconnected. To distinguish between the ground and the neutral bus bars on a panel board, an inspector can look closely at their connections to the body enclosure or box of the panel. Ground terminal bars are screwed directly into the metal body of the panel. Neutral terminal bars are insulated from the panel body, usually by plastic standoffs. Main service panel boards must be bonded to the grounding system, but there is also a very long list of other components that need to be connected to the ground since they have the potential to become energized by electrical faults. These include interior water piping, water heaters, around water meters, gas lines, electrical enclosures, electrical raceways, electrical outlets or junction boxes, and CSST gas piping, and then telephone and cable TV systems. Bonding piping, the metal gas and water piping in the house must be connected to the ground must be connected to the ground bar in the panel. This connection is called bonding. The wire making the connection is called a bonding jumper. We bond pipes because if a metal pipe is energized inadvertently, the bonding jumper provides an easy path back to the source so that enough current flows to trip the breaker. Refer to the illustration where the metal water pipe, where the grounding electrode is connected to the metal water pipe near the water meter. Inspectors should check for a bonding jumper wire that crosses over the water meter. Inspectors may observe metal water lines bonded at the water heater supply pipe and the metal gas pipe that are as close to the panel board as possible. For a 200 amp service, the code calls for at least 6 gauge copper to bond metal gas pipes and 4 gauge copper to water pipes. At the main service panel board, the 2 ungrounded hot service conductors from the meter base attach to lugs or terminals at the main breaker. The incoming grounded neutral service conductor attaches to the main lug of the neutral bus bar. In a typical electrical service panel board, the neutral bus bars are bonded to the service panel board enclosure by means of a special bonding screw or strap provided by the equipment manufacturer. That component is called the main bonding jumper. We use the term jumper, but the main bonding jumper could actually be a wire, a strap, a bus bar, or a self-tapping screw. If it's a screw, it usually has a usually green in color to clearly show its purpose. The main bonding jumper should not be spliced. The main bonding jumper is the primary connection between the grounded circuit conductor, the bare stranded service conductor in the illustration, and the equipment grounding conductor, commonly called ground wires, where the conductors are usually bare copper or green insulated wire, or the service entrance or the service equipment, which is the supply side, bonding jumper, or both at the service. The main bonding jumper connects the service neutral wiring to the grounding electrode conductor and also to the service panel board cabinet. The main bonding jumper is a reliable conductor that ensures the electrical conductivity between the metal parts required to be electrically connected. All right. This is more examples of your main bonding jumpers. So you got the green screw there, your main bonding jumper. And then this strap here, can you guys see my my mouse?
We can see it. Yeah, we can see it.
Okay, so you can see there that that's the main bonding jumper, the bent metal piece. Okay. All right. These show different types of panel bonding. Some are straps, some are screws. So you can see all the differences that you'll see in these random panels. A lot of metal straps, a lot of green screws. All right, in more modern panels, the bonding connector is required to be through an approved green screw, so it is more apparent to both the electrician, the code enforcer, and the home inspector. In the service equipment, and only in the service equipment, just like the main electrical service panel board shown, at the location of the main disconnect, the grounded service conductor, the bare stranded neutral conductor in the illustration, is connected to the same neutral bus bar as the equipment grounding conductors, and possibly one or more grounding electrode conductors, such as the green wire, that goes to the grounding rod outside or a metal water pipe. Therefore, the neutral bus bar can function as a main bonding jumper because it is the connection between the grounded service conductor and the equipment grounding conductors. In the main service panel board, the equipment grounding conductors, or the ground wires, attach to the grounding conductor terminal bar, which is bonded to the metal panel board cabinet by the main bonding jumper. Attached to the grounding conductor terminal bar in the service panel board is a large, sometimes bare or green copper ground wire called the GEC that clamps to a grounding electrode, such as the driven ground rod or a UFER. If there is a ground fault in the house, the main bonding jumper ensures the current can be safely directed to the ground away from the house and the people inside. The main bonding jumper provides a low impedance fault current path back to the power supply to facilitate the tripping of the overcurrent device in the case of a ground fault. Grounding is the single most important component of a building's electrical system, and the main bonding jumper is the single most important connection in the entire electrical system. As I'm going to turn on my light quick. All right. So at the main disconnect, all neutrals and grounding wires are combined and connected and bonded to the panel cabinet. If the main bonding jumper at the main service panel is a green screw, it should be screwed down with little to no thread shaft showing, unlike the one in the inspection image. On some older panels, the main bonding jumper screw is not green and may take additional investigation to look. Let's see. In this image, the main bonding jumper is properly not screwed down all of the way. This is properly installed because the panel is a sub-panel, not a main service panel. You can see the neutral wires. Okay. Oh, wrong one. All right. Service panel boards. Service panel board is a distribution or load center that contains the main disconnecting means. This is the only panel where the neutrals and the grounds should be bonded together. Distribution panel board or subpanel are downstream from the main panel containing the main service disconnect. In these panels, the neutrals and the grounds should be separated and the neutral bus should be isolated from the panel enclosure. The only exception to this is an existing detached structure where no metallic path exists between the structures. In this exception, a connection between the grounding conductor and the metal case via a bonding jumper is permitted. According to 2008 NEC, this is not allowed in new construction. So in all cases, a 4-wire feed to the detached structure is required in order to isolate the grounded conductors from the equipment grounded conductors. All right, 2 methods. You have a 4-conductor feed or a 3-conductor feed. 4-conductor feed, you have the 2 hot or ungrounded conductors, 1 neutral or grounded conductor, and then one grounding conductor. And then the 3-conductor feeders, you have the 2 hots or ungrounded conductors, 1 neutral or grounding conductor, and then the equipment grounding through the conduit tubing, electrically linking the 2 panels. In my area, if you have a main panel, or if you have the meter and then the main panel in the yard, and like in the back easement, you have to have 4 wires coming to the house, according to our state electrical inspector. All right, an important note. Every structure is required to have a grounding electrode system. If they are present in the structure, they must all be bonded together. If a detached structure has a remote distribution panel located at the structure, then it requires a grounding electrode system of its own. The equipment grounding conductor in a 4-wire feeder does not take the place of a required grounding electrodes. It is also important to understand that if the detached structure is being fed by a single branch circuit and it contains an equipment grounding conductor that is used for grounding the non-current carrying metal parts of the equipment, then no grounding electrode system is required. The inspector should pay very close attention to grounding and bonding of all electrical circuits. Sometimes it's very hard to figure out which components are electrically connected to others. When in doubt, recommend a licensed electrician. All right, let's see. Oh, let's take another 10-minute break before we watch this video, and I will make sure this video is up and running before before you guys come back. Robert Lamb asked the question, is there a main service panel bonding change when you have a solar system? No, nothing should be changed or affected on your main service panel. Now, you can definitely have if you have a solar, I guess it's mainly just a solar and generator, you can have a connection via a different breaker on your, okay, so say you have a meter and your disconnect on the side of the house, you should have a breaker there, which can feed your generator, your solar, but then that goes to the generator, and the solar should have its own panel. Because those systems can potentially backfeed electrical service back on the electrical lines, there should be safety I want to say I can't think of the terminology. There should be a device that prevents electrical current from flowing back onto the power lines. So all of that should be contained in the system that is dedicated for solar and for generator. Do you need GFI outlets on arc fault breakers? Let's see. So you need GFIs in all water locations. And so what's happening in NEC is that there's a lot of locations that are now requiring double protection for both AFCI and GFCI. So arc fault is only going to protect against break in the wire, loose connections, screws and nails in wires and stuff like that. It is not going to protect against moisture. So do you need GFI outlets on arc fault breakers? It depends. If that arc fault breaker, if that area, let's say you have a bar in a house. A lot of times that bar is going to be in the living room, and that living room is required to be arc fault protected, but now so is that now it's also protected, or it needs to be protected with GFI because it's in proximity to water. What is the process for inspector when all kitchen circuits are on a series and not individual GFCI plugs? Some trip the circuit but cannot find the main switch. So Robert Lamb asked, what is the process for inspector when all kitchen circuits are on a series and not individual GFCI plugs? Sometimes you trip the circuit but cannot find the main switch. So, GFI, I think I understand what you're getting at. So GFI outlets have to have a load side and have a service side. So the wires, so the service that's coming into the outlet has to come in on whichever side the outlet stays, right? So if it's on this side, then the surface side has to come in on this side, and then the load side has to exit on this side. A lot of times you'll see where a DIY homeowner will flop those wires on opposite sides of the outlet. And so while this outlet itself is protected, sometimes it's not going to protect as intended the outlets that are downstream from the outlet itself. So you'll often see that if you have multiple testers and you have one GFI on a countertop, and then you plug in your tester here, you plug in your tester at the outlet that's downstream from there, you expect it or anticipate it to be downstream, and you trip it, and the outlet stays active, or the outlet trips here on the GFI, but the outlet downstream does not trip. So then you're like, okay, well, maybe it's on the GFI, and you go and check all the outlets, and none of the other outlets trip power or turn off power to that outlet. And that usually means that the wires are not on the correct side of the GFI outlet. So pay special attention to that. And then, I will say electricians, depending on how they feel that day, they will wire their GFI outlets to protect a smattering of different circuits or different locations. So, you can find upstairs bathrooms protecting downstairs bathrooms or vice versa, or you can find a downstairs bar area protecting an upstairs bathroom and vice versa. So it's an investigation. You have to be Inspector Gadget and try and figure out, what is going where, making sure everything is tripped and protected the way it's supposed to be. Looks like we're ready to go. So, all right, I think the video is up and ready. So here we go.
Different types of grounds
Oh, sorry.
I'd like to talk to. In the Chicagoland area, we use water pipes. And think about it, you got miles and miles and miles of underground steel, lead, copper, unlimited pieces of metal that's underground, which are fantastic conductors and are going to allow everything to flow quick and easy. We're still going to be limited. All right, that's still going to only limit 5 amps of electricity to flow because it still has to get from that over to the transformers. So getting from those 2 points is where our resistance is going to end up being. Right? There's just not enough electricity to flow to clear the path. Right? Different types of grounds. Let's go back to this one here. And different types of grounds that we're going to run into. So here it mentions the water pipes. We already talked about the ground rod outside. Some areas of our country, they don't have soils where they could dig into. Sometimes they're on bedrock and they can't take that piece of steel in there. Sometimes it's going to be on a slab. Different things that we can use for a good connection to the earth, item to earth. Well casing. All right, so if I got a metal wall casing that goes down, I could ground to that. I could do something called a ground ring. So I would end up taking a number 6 or a number 2, depending on the size of the electrical system, and it would be a bare copper wire buried about 1 foot underground, going around the entire perimeter of the house. That's called a ground ring. A ground plate is basically a 4x8 sheet of metal laid flat, covered in dirt. All these are good connections. An oofer ground is another one. That's where I use the steel rebar that's in the concrete. And I'm going to use that as my connection to the earth. All of those are acceptable, all right? And all of those are going to help me dissipate lightning strikes, and then they're all going to also help me maintain it. Bonding, on the other hand, we talked about item to item. When we talk about the main bond, all right, or, I hate to do the quotation mark things. When we talk about the bond, that's going to be located at the first means of disconnect, right? That bond is going to be connecting 2 distinct items. So we said bond is item to item. When we're talking about the bond or the main bond, we're connecting the grounding system to the neutral system. We're doing that so that if I do get a ground fault anywhere, that's going to allow free flow electricity, and we're going to basically change it into a short circuit. And that's going to be tripping the breakers. Without that bond, we're just going to be flowing electricity into the earth. We're not going to have enough flow to go ahead and trip the breakers. So that bond is vitally important. When we open up our panels, the first thing that we're going to look for is the bond. I want to verify that I got my ground connection to my neutral connection. That's how I know that if there's anywhere, at least I got some sort of a pathway, maybe. I have a pathway at that point in time to get it onto the neutral system. After that, the next thing I'm going to be looking for is my grounding electrode conductor, all right, or my GEC. That is also known as my ground wire, but that's a specific ground wire, all right? That's going to go from the location where the bond is to wherever I'm going to be grounding this to. So whether it's a ground rod, whether it's a water pipe, ground ring, oofer ground, ground plate, well water pipe going in there, whatever I'm grounding my house to, that GEC is my connection from the main, where the main disconnect, it's my connection from there to whatever I'm grounding to. That grounding electroconductor does have some specific rules to it, right? And I don't have them written down. So if you have a pen and paper, I would suggest that you write the following down. I'll try and go a little bit slow. Depending on the size of the electrical system tells me the size that that GEC needs to be. GEC, grounding electroconductor, all right? If I am less than 150 amps, then that could be a number 6 copper wire. Less than 150 amps, a number 6 copper wire. Greater than 150 amps, it needs to be a number 2 copper wire. 150 amps or more, I should say, it needs to be a number 2 copper wire. That GEC is not allowed to have any splices in it whatsoever, all right? So when I identify it, and I follow the conduit or I follow the GEC going wherever it goes, I want to make sure that it's not cut and I don't have 2 connections under a mechanical splice. I'm not allowed to do that. There is one way or one type of splice that I could do. It's called a pressure splice. And they'll put a hydraulic tool on 2 pieces of wires and they'll squeeze the living daylights out of that thing until they melt it into one wire. All right. So there's no screws, there's no mechanical connection. They just squeezed it and basically made it into one wire. We'd have to literally cut it with cutters in order to break that connection again. So if we could break a connection with the screw, it's wrong. If we have to cut it, then that splice is okay. And those splices don't have to be in a junction box. So as I follow that out, if I run into a junction box on my ground pad, I should be suspicious. And those are going to be the areas that I'm going to open up. And if you get inside that thing and you see your GECs are spliced together, that's a problem because we're not allowed to splice those whatsoever. They have to be, if they're going to be in conduit, they have to be in conduit by themselves. All right, we can't use that raceway to share with other electrical wires. They have to be standalone all by themselves. So if I'm having trouble finding my GEC and I'm inside the panel, one of the things I could look for is in my conduits, there should only be one, maybe 2. You know, if they go one to the water pipes and one to a ground rod outside, I might have 2 of them. But they should be one wire inside that conduit all by itself. All right. If any other wires do share and go in there, that's going to end up being a problem. Nothing else goes in that GEC by itself. If the GEC has insulation on it, all right, then that should have a mechanical connection because we want to use the conduit as well that protects the GEC. We want to use the conduit as part of our grounding system. So we need to have a mechanical connection pretty much at both ends to the conduit. If it's not does not have insulation, so it's a bare conductor for the GEC, and you will run into those are not required to have a mechanical or a metal connection at each end. So we don't have to tie it to the conduit. It makes sense because obviously if it's bare through and through, then most likely it's going to be touching that conduit in multiple places that comes in there. So no splices, number 6 or number 2, 150 amps is my line in the sand. Nothing else shares in the conduit with it. In Chicago, we have something called a Chicago ground, and they did that in a lot of the suburbs around here as well. So they'll come out of the electrical box, usually at the first means of disconnect, and they'll go to the closest water pipe. And when they get to the closest water pipe, then that's where they're going to attach their ground system or grounding electroconductor to that water pipe. From there, I need to follow that water pipe until I leave the building. If I have any sort of dielectric unions, or I'm switching to plastic pipes or something like that, I've lost my grounding connection. So I have to have jumpers over those if need be. When I get to the water meter, I want to make sure I'm jumping over the water meter as well, because there's going to be a time when the water meter might, if the house gets foreclosed and the water meter gets removed, we don't want the person who's going to be connecting it together. They're going to touch one side that's going to be 0. They'll touch the water main that might be something different. And once they touch those 2 different objects, if they're different potentials, then the electricity is going to flow through them before they put it together. So we need to have a jumper cable that's loose, connected. When I say loose, I mean the wires aren't wrapped around it really tight. The connections are tight and secure. We should actually be moving those and make sure that they're tight, so that I know I got a good connection between the between both sides of my jumper cable. Now back to neutral to go ahead and clear the fault path. Good. So there's our bond screw, and these are just different examples of what we're going to see on the bond. And again, we're tying right below that. It's going to be my neutral bus bar. So this whole thing over here is my neutral bus bar. And there you can see where my bond screw is. So that screw goes through that metal bond or metal bus bar. It goes through the black plastic insulation right there, and it ties into the metal box that's behind it as well. Now that metal plate runs behind the neutral and the energized conductors, and then it also ties into this neutral bus bar on the left-hand side. That is my bond. So if anything energizes my grounding system, that's going to allow electricity to get over to my neutral system, and then I'm going to have free flow electricity enough to go ahead and trip my breakers. This is known as a bond screw. Sometimes we're going to see a bond strap in here as well. That's this item down here. So that bond strap, again, goes into the neutral bus bar, ties to my box. Any electrical wires that come loose and interject. See that mark? I'm going to bring that up in a second. Anything that's tied to both. Anything that ties the bolt again are going to go ahead and connect it. So if any energized conductors come loose, energize my box, then it's going to go ahead and energize my neutral. Right. We do have one question up here. And let's see if I can pop this on here. That's not play nice to me. All right. So one of the questions Mark asked, if the water pipes aren't used for grounding, then is it still important to jump past the water meter? And the answer is going to be yes, because even if the water pipes aren't used to it, if I have, and especially in our area, if I have a water meter there, it's very common. So the utility companies are going to be expecting to use that as well. If the utility companies, such as the phone company, cable company, satellite dish, they all have to ground their items as well. So they may be going ahead and grounding to the plumbing pipes. They may go ahead and ground to the meter box outside. Whatever it is, the expectation is there that those items are grounded. Not only that, but if somebody is outside and they're going to be touching the plumbing pipes inside and something's disconnected, we want to make sure, because all those pipes are metallic. I'll even go one step further. You know, we should actually be bonding our water pipes to our gas pipes. In some communities, they do that, but in many communities, they don't. And the whole idea there is, again, if somebody touches the gas pipe, because they usually run right by the water pipes, if they touch both of those, we don't want them to be different potential. This is a pushmatic panel, and some panels are really difficult to be able to find that bond screw. It's not always going to be that big, fat green screw or that bonding strap that we saw earlier. This one here, where that arrow's pointing, that's actually my bond screw. It goes through the neutral bus bar, which is all those screws above it, and it goes into the panel in the back. There's going to be a schematic, unless it got pulled away or damaged or whatever. There should be, I should say, a schematic on every panel that shows the neutral bus bars, the breaker bus bars, and on there you're going to be looking for a phrase on there that says bond when required, and it's going to be pointing to a certain hole or slot. That screw needs to be filled in there. Now, we're not going to know if they put the right screw in there. Somebody could have put the wrong screw and it doesn't go all the way through. We're not going to back these things out and verify it, but we should be able to verify that most likely it is there. In this case, on the pushmatics, that little screw there to the right of the GEC That's gonna be my bond screw that comes in. Here's our typical water meter. This is a lead service main coming in here. As we come up, you can see I have my GEC, my grounding electrode conductor. It does have insulation on it, so the insulation is stripped back. That wire is not cut. Remember I said we're not allowed to cut or splice this GEC at all, right? So it's not cut, but the insulation is stripped back. That strap that's on there connects it to my conduit, and it also makes a solid connection to my water pipes on the street side of the meter. Again, the connection where the wire is fed underneath there, the insulation is stripped away, but it's not cut, and then we jump over to the left side of the meter. Something else too, just throwing this out there, that tamper wire on that water meter, you know, I kind of look for those. Many times you're going to find a tag on there where it's like a $500, $750, or $1,000 fine if that tamper wire is cut. And I can't tell you how many times, actually, I would guess to be around 20%, so 1 out of every 5, I find where either that tamper wire is missing or it's cut. Some communities don't require it, and some do, all right? But I would still let my client be aware of it. This way, they're not going to get stuck in case for some reason a meter reader comes inside and sees that that's missing. But for us, in this class, we're talking about the GEC. That GEC, in this case, it's probably about 100 amp service, because that looks like a number 6 copper wire. And it needs to go to the street side of the meter and jump over the meter. This one here, same thing. We connect it, we're on the street side, but we don't have a jumper wire coming back. So here's another view of the same picture. Our water line's coming in, we're connected to the street side, but I don't see anything that is taking it from this side of the meter over to this side of the meter. And we should have some sort of a jump. Also, remember what I said about the tamper wire. This one was also cut. I think this is a great practice as well. I'm seeing it more and more communities, which I'm pretty happy with. So they'll jump over or bond both the hot and cold water side of the water heater. Usually I'm seeing that same wire will continue on and go to that gas pipe that's to the left. So they'll put all 3 of these together and make sure they're all the same potential. And again, if somebody has to switch out this water heater, once you remove that water heater, you break all the bonds of those different items. Not to mention we got dielectric unions on the water heater as well. So these dielectric unions that you see down here, those have little plastic pieces that separate that in there. So I really don't even have a connection to my water heater at this point in time. The electrical potential and all the connected metal parts needs to be the same as the earth, plain and simple. Anything that's different, we're going to take a chance for electricity to flow through a human being. We don't want that to happen. So we need to maintain that we're properly grounded so that we keep that 0 potential. Lightning strike, same thing. I want to give a pathway for that electricity to get into the earth. Subpanels. All right, and this is another important one. We do not want to combine or bond our grounding system to our neutral system in a subpanel. We should have separate grounding conductors and separate neutral conductors when we come through it. The reasoning goes back to the amperage not disappearing. So if I'm inviting amperage to go on the neutral, and we'll get back to a slide to show that a little more clearly. In fact, here it is. Let's start building it, and then we'll talk about it. So I got an energized conductor on a breaker, phase A. I go ahead and connect it to my bus bar and my subpanel. I take phase B, connect that to my bus bar on the other side. So now my panel's got a 240 panel on the right side. I'm using the disconnects in the bottom of the left panel in order to make all this happen. I run a separate neutral wire. Everything is good at this point in time. I'm going to bond and ground my main panel at that point in time. So I just popped the bond up there, and right before that, I put the GEC. Now I have a regular electric circuit. We have a hot and a neutral going to it. I'm still in a conduit system, so my conduit will be my grounding system. We're going to keep everything separate at this point in time. All right. So energy goes in through the hot, comes back on the neutral. The amperage is still flowing on the neutral. Neutral goes up and out. No problems, normal conditions, nothing, no problem whatsoever to see here. So now what we do is we're going to throw a bond on the sub. And again, this is going to be under normal circumstances that's happening here. So what we're going to do is energize that outlet again. So we're going to be doing work. Amperage does not disappear. So we're going to energize our energized conductor, and then amperage will be on the neutral. Amperage or electricity is going to flow in any means possible. All right. So yes, it is going to flow on the neutral. No doubt on that. But because I'm bonded there as well, I'm putting a connection to my electrical panel. Electricity is also going to be flowing on my electrical panel as well. All right. So now I'm going to have amperage where everywhere between, as long as electricity is flowing and how much amperage is being used, I'm going to have amperage on my conduit system between the panel and the sub panel for whatever is being used. And if somebody touches that and something else that's zero, then they can go ahead and start creating an ulterior flow, and they can actually get the pump shock or electric fluid. All right. So having that secondary bond, I'm sorry, it's not good. All right, plain and simple. Now, either way, with or without the bond, if I had that ground fault and everything else was connected, all right, I would still be good. So here we're showing the case fault, energizing my case, energizing my panel, energizing my conduit, energizing the other case, energizing my bond, and that gets my power to the neutral, free flow electricity. My breaker is going to go ahead and trip. This is all good, so it's not going to harm us there. But the biggest problem is we're inviting electricity under normal usage, not under a fault usage.
All right, so I hope that answered some of your questions that were in the question and answer feed about separating the grounds and the neutrals, especially for Kenneth Blair and that 3-wire feed. Let's see here, who else? We have a lot of generator and solar questions, gentlemen. I'm not going to be able to answer solar and generator questions today. Like I said, I think if you have solar or a generator, that should not change anything for your main service panel. Now that will change stuff, in your sub panels, your distribution panels for sure, but that should not change anything on your main service disconnect. Talking about generators and solar panels, would be an advanced electrical class. That is not what we're going to be going over here, and so I apologize, but we'll have to skip those questions for now. So going back to panel board and cabinet, most panel boards used in 1 and 2 family dwellings come from the manufacturer already. Come from the manufacturer already installed in a cabinet. In this article, we use panel board to refer to both the panel board and its cabinet. Many inspectors, contractors, and electricians refer to the panel board and cabinet together as the panel or the breaker box or the breaker panel, and do not necessarily distinguish between the cabinet and the panel board. For simplicity, home inspectors could use the term panel board to refer to the cabinet and the panel board as a unit. Panel board size. Panel boards or breaker panels are measured by their maximum current carrying capacity given in amps and by the number of circuit breakers they can hold. Code requires services be at least 100 amperes for homes. Generally, the most homes smaller than 3,500 square feet that are not heated electrically, a 200 amp panel with 40 breaker spaces provides enough power with some room for expansion. Panel boards should be mounted as close to where the service entrance cable enters the house as possible, but not always. When the panel board is mounted in a basement, the panel board may be observed attached to a piece of plywood. The wood provides a flat, reliable surface for mounting the box and stapling the cables within 12 inches of the box, or as your local code requires. Panel board basics. I'm gonna get rid of this here. That other gentleman in that webinar kind of went through all this stuff already, but you can see here the service panel board shown below will be the only point in the electrical system where the ground wires and the neutral wires are bonded together. If there were a subpanel after this, that is where the main bonding jumper, this guy over here, would be disconnected, and the neutrals would be isolated off the panel, and all the ground wires would be terminated on the ground bus over here. Let's see, for commonly installed 200 amp service, the SEU service entrance cable between the meter base and the main electrical panel board will have two 4-aught aluminum conductors for the HOTS and a bare 2-aught aluminum conductor for the neutral conductor. Each ungrounded hot conductor terminates at a breaker or fuse in the main disconnect, which is the first means of overcurrent protection. The main service disconnect is housed either in the distribution panel or in its own separate box. In the image shown, the integral main service disconnect is housed at the main service panel board. The ungrounded hot service conductor ends terminate and are connected to the main terminals of the main service disconnect. The main disconnect is a large 240 volt circuit breaker located at the top of the panel board, or it could be at the bottom. It controls all power entering the home and connects to both hot bus bars running down vertically through the panel board. If the electrical service utility is connected, these main terminals will be live even if the main breaker is turned off. The bare stranded grounded neutral conductor connects to the neutral bus bar. The location of the neutral bus bar varies depending on the panel manufacturer, but it is always separate from the two hot bus bars. The neutral bus bars are long aluminum bars containing many holes with terminal screws to which ground and neutral branch circuit wires are attached. And there is one larger hole for the main service grounded neutral conductor. All the connections should be secured with the use of a torque wrench. I've been around a lot of electricians, and I don't think I've ever seen them pull out a torque wrench. The service entrance conductors at the connection point with the main terminals or lugs may be coated with antioxidant according to the manufacturer's recommendations or the local code. Panel board manufacturers since the late 1940s are approved for aluminum terminations and do not require antioxidant paste on the terminations. Home inspectors may observe antioxidant applied, but it is not required. Main disconnect breaker is the master switch for the panel board. It shuts off power to the everything downstream, including hot bus bars and all breakers mounted to them. All electricity entering a house goes through the main breaker. In an emergency, this main disconnect can be turned off to turn off all power to the house. The main breaker is the primary overcurrent protection device for the electrical system and is rated accordingly. Whenever it's installed, the center of the grip of the main disconnect must be readily accessible and no higher than 6 feet 7 inches above the floor, ground, or working platform. The rating should always be stamped on the breaker handle, and the metal bus bars run from the main breaker down the middle of the panel board to distribute the power to the various breakers. Here's the disconnect rule that somebody had asked about previously. Yes, you must be able to turn off all power to the house with at most 6 hand motions. Each panel board should have only one disconnecting means, and the maximum number of disconnects should not exceed 6. We're going to go over a few breakers or panels later about a split bus and how they're not ideal or not recommended. The reason being is that a lot of times those split buses will have more than 6 disconnects. Hot bus bars, those are those metal bars that run down the center of the center of the panel. The neutral bus bars are generally on the sides or on the bottom. You'll see them in older panels on the bottom in a big group. And then the grounding bars. Those could either be on the sides of the bus or on the sides of the the hot bus bars, or they could be isolated, or not isolated, but bonded or bonded to the side of the panel. All right. Circuit breaker panel boards. These are probably the most common types that home inspectors will come across. They have replaced fuse panels since 1960. Circuit breakers are far from being perfect safety devices and require some testing and monitoring. Breaker panels go back farther than many people realize, were patented in 1910. However, it is unusual to see a residential breaker panel from before 1940. Prior to this, electrical breakers were primarily used in manufacturing and naval applications. Breaker panels started appearing in homes in the mid-1950s in small numbers and were universal in most areas in the United States and Canada by the late 1960s. Circuit breakers did not replace fuses due to any deficiency of the older technology. The problem was that when a fuse blew, a person had to go find a replacement. Breakers are obviously more convenient because when they trip after a fault, they can be reset without replacement. Now, we have added benefit from circuit breakers with the advent of both ground fault circuit interrupters and arc fault circuit interrupters in many locations. Circuit breakers are the most commonly used form of overcurrent protection in residential wiring. The code requires that an overcurrent protection device, like a circuit breaker fuse, be installed in series with each ungrounded conductor, which is the hot wire, at the point where the conductor receives its supply inside the panel board, except for service entrance conductors. Circuit breakers fall into 4 categories: 240 volt, 120 volt, GFCI, and AFCI. All of these require some specialized knowledge to properly evaluate. Remember, we are talking about energized components. Safety is paramount when investigating electrical panels and overcurrent protection devices. 240 volt breaker has 2 handles that must move together. Sometimes you'll have one handle that's on a double slot. So there must be some device like a clip or a pin that makes the 2 handles act as one or move together. Also, tandem breakers that are on a multi-wire branch circuit should all have handle ties, although this has not always been required. It is not proper to have a piece of wire, going from connecting 2 breakers. You've seen wire, basically anything that it can fit in that hole, you'll see it. So it should have a proper tie on it. Common 120 volt circuits are fed from one bus bar only. Also in use are tandem breakers, which are 120 volt breakers that feed 2 separate circuits, each controlled by its own handle. These should not be linked. As with fuses, the inspectors could check that the rating of the breaker does not exceed the rating of the conductors unless allowed by code. Otherwise, something other than the breaker is likely to overheat and fail. There are 2 manufacturers of single pole 120 volt breakers who have their products listed for 2 conductors. These are made by Square D and Cutler Hammer. These should not be confused with double tap breakers, which are more than one conductor has been incorrectly connected to a single breaker. GFCI breakers, stands for ground fault circuit interrupter, are a way to protect circuits and people from ground faults. Not all circuits are required to have GFCIs in many homes. The locations that require this protection have their own GFCI receptacles. However, if a GFCI breaker is installed at the panel board, it will provide protection to all receptacles downstream from the breaker in that branch circuit. AFCI and GFCI breakers have integral trip and reset buttons to help ensure that they are working properly. The home inspector should trip the breaker using the test button and ensure that the circuit has indeed been switched off. There's a caveat to that. If the home is lived in, and especially if someone is home, you want to check with the homeowner before tripping any of those devices, because they might be in the middle of a meeting, a webinar or a Zoom or whatever, and if you trip that breaker, it can make them very irritated. So, arc fault circuit breakers, circuit interrupters have been required in new construction since 1999. Many jurisdictions are now observing recent code additions, which have expanded the use of AFCI devices to almost everywhere within a dwelling. I opened up a panel the other day, and the entire panel had some kind of AFCI or GFCI or combination breaker in there. It's a very expensive panel. These breakers are designed to trip if they sense arc faults in the circuits, which are caused primarily by damaged wire. In the 1999 NEC, those breakers were required only on bedroom receptacles. In the 2002 NEC, they expanded to all 15 amp and 20 amp single phase 120 volt branch circuit supplying outlets. The 2005 NEC expanded their use to allow AFCI devices similar to GFCI receptacles, but none existed on the market, and their use was limited by different code. Finally, in the 2008 NEC, the use of combination type AFCIs expanded to 15 and 20 ampere branch circuit, supplying outlets installed in dwelling units for family room, dining room, living room, parlor, library, den, bedroom, sunroom, recreation room, and similar rooms, including hallways and closets. Many people confuse the term combination to mean AFCI and GFCI together in a single device. This is partly correct in that most AFCI devices offer Class B of GFCI protection, which usually starts at around 20 to 30 milliamps, and do not offer any personal protection as do conventional GFCIs. The combination type AFCIs are designed to activate when there is a parallel arc that reaches a peak of 75 amps. The combination refers to the fact that AFCIs are now protect against series arcs as well. They have 5 amp peak threshold. This is where the term combination comes from. Remember, the term outlet is not interchangeable with receptacle. Outlets are defined by the NEC as a point on the wiring system at which current is taken to supply utilization equipment, meaning recess lights, smoke alarms, receptacles within outlet boxes, and so on are supplied from outlets. It is likely that many more locations, maybe even the whole house, will be required to have arc fault protection with future code revisions. As with GFCI breakers, these should also be tripped with their test buttons, and the circuit should be checked to make sure it has been shut down. The inspection image shows a pair of AFCI breakers. Notice the test buttons, and also the second conductor that connects the breaker to the neutral bus bar. This is not a double tap. Some early square D AFCI breakers had to be recalled due to manufacturing defects. Currently, however, many AFCI manufacturers are in their multiple year generation and are proving to be worth every penny when saving lives and property. These identified breaker, the pictured breakers that you see there, there was a known defect with those breakers. So you have that teal button. A lot of times that button went faulty shortly after installation. So keep an eye out for those guys. All right, the inspector should pay special attention to the following questions and report any deficiencies as in need of immediate repair. Does the breaker exceed the capacity of the conductor? Does the breaker have multiple incorrect taps? Do the 240 volt breakers have their handles tied properly? Do the GFCI breakers test and reset properly? Do the AFCI breakers test and reset properly? Is there any sign of overheating, arcing, or smoke damage on any of the breakers? I would recommend, if your local supply house will do this for you, that you go and get all the different sizes of wire and label them with the size of the wire and the amperage that it's rated for. I did this on both for aluminum and copper. This will help you greatly in identifying correct wire sizes in panels. All electrical systems require a means of disconnect so that the service can be shut down quickly if any dangerous conditions exist. The service equipment is the necessary equipment, usually consisting of a circuit breaker or switch and fuse and their accessories connected to the load end of the service conductors to a house and intended to constitute the main disconnecting means for service. The disconnecting means for service should be located outside or inside the house as close as possible to the point of entrance of the service conductors. The service equipment must be identifiable and marked as a service disconnect. A common service size for a single family house is 200 amps, and the main 200 amp breaker located at the main panel board would be the main disconnect for the service. There are different types of disconnects depending on the age of the property. Again, the rating or fuse or breaker size of the disconnect relates to the total amperage available within the home. If the main disconnect is, for example, rated only at 100 amps, it doesn't matter that the SECs, the service entrance conductors, are rated for 200 amps. Real quick, types of disconnects. Talking about the knife switch over here. I had an electrician call me earlier, and he wanted me to just briefly mention that the knife switches that you get oftentimes for solar panels or for generators, and so I know I said I wasn't going to talk about that, but you should make sure that that panel cover is always can be secured somehow with, because a lot of times, depending on the brand that you use, those panel covers can be easily removed, or if the unit is switched off, the panel cover can be removed. But just because it's switched off doesn't mean that that panel is does not have power to it. So little side note there. All right, split bus panels. What we were talking about, the 6 means of or the 6 hand movements. So the six hand movements to completely disconnect. That's where this comes in. Some panels are of a split bus design, which means that the bus bars that the breakers draw power from do not extend right through the panel. Normally, these panels will have a multiple double pole breakers at the top of the panel, controlling the 240 volt circuits, such as your dryers, your stoves, your air conditioning unit, and then your single pole 120 volt below that. So where that comes into play, that 6 hand movement is, if there's more than 6, if there's more than 6 breakers with that 6th breaker disconnecting the power to the lower breakers, then you might have an issue. Where that came into a problem is if somebody took out a 240 volt breaker on that top bus bar and replaced it with 220 volt breakers, then now you have 7 disconnects. So just keep an eye out. Remote disconnects, main panels and subpanels. Many homes and nearly all mobile manufactured homes, the service disconnect is not in the main distribution panel. This is not a problem, but care must be taken to fully understand the grounding and bonding of all downstream distribution panels. In terms of grounding and bonding, the neutrals and the ground should be bonded, connected at this cabinet, and disconnect only. Remember that the panel with the main disconnect is the service panel, and the panels downstream or on the load side of the service panel are distribution panels or subpanels. Neutrals and ground should be bonded together only in the service panel and not in any downstream distribution panels. There's a fight with our local AHJs around here and the electricians. We've had our local AHJ code inspectors had to be corrected by our state code inspectors. So the local AHJ code inspector was allowing for bonding. So if you have, in this specific instance, you had a meter and the main disconnect in the easement in the backyard, went into a service panel on the side of the home. That service panel is supposed to have the grounds and the neutrals separated and the neutral isolated from the panel and the ground bonded to the panel cover. The local AHJ, he passed it. Then it got pushed up to the state code inspector, and he corrected all of our code officials in my area. So while a lot of that probably went unnoticed for years, that you'll find that where it was a requirement, the local AHJ guy and the electrician did not follow the state regulation. 100 amp service minimum for houses serving only one family. The ampacity of the ungrounded service conductor shall be a minimum of 100 amperes, 3 wire. For all other installations, the ungrounded conductors should have an ampacity of at least 60 amperes. The ungrounded service conductors should have a capacity of at least the size of the load served. According to our standards of practice, the InterNACHI standards of practice, the inspector shall describe the main service disconnects amperage rating if labeled, and that's all the home inspector needs to do here. Reporting the disconnect's amperage rating is important for two reasons. First, an older home may not have enough power for a modern family's needs. Second, many insurance companies will not insure a property with less than 100 amp service. When homes were first wired for power, there were few electrical devices available, so a couple of 15 amp lighting circuits may be, and maybe a radio outlet were all that was needed. Obviously, the modern age, and since 1960, we have gotten much more ambitious with the use of electric power. Just about every room in the home has multiple appliances in it, and we need higher amperage 240 volt circuits to run systems such as central air conditioning and electric clothes dryers. In many cases, the listing information about a home may not be correct regarding the service amperage because brokers or owners rely solely on the size of the main breaker or fuse. Many people are also under under the mistaken impression that the total available service amperage is the total of the individual breakers or fuses of the service panel. One way for a home inspector to help communicate the available amperage is to determine the ampacity of the lowest rated or the weakest link of the following components: service supply, electrical meter and the socket, service entrance conductors, service disconnect, or the distribution panel. Here's a couple of examples. A home inspector should describe, and the examples are here on the slide. A home inspector is not an electrician. A home inspector must be careful in describing the total amperage service supply to the house. A home inspector must follow the standards of practice and be careful in exceeding those standards. Refer to the InterNACHI standards of practice. All right, 3-wire SEU. Take a look at the following illustration. The 3-wire SEU service entrance cable runs from the meter outside of the house to the main electrical panel. The main panel board contains the main service disconnect. The neutral wires, white, and the grounding wires, green or bare copper, from the branch circuits terminate at the neutral grounding bus bars. The removable connection bar connects the two neutral grounding bus bars, and the main bonding jumper connects all of that to the panel cabinet. In this common installation, the neutral wires should not touch the grounds anywhere in the house except here in the main disconnect panel board. This is a safety feature that provides a separate path to ground from the neutral conductor. The ground wires of the individual branch wires of the the ground wires of the individual branch circuits can all be connected to the same grounding bar in the main panel. The ground wires carry the ground to each and every device, fixture, and appliance in the house. At the illustration, you can see the main service disconnect panel board, the two hot cables from the meter base attached to lugs or terminals on the main disconnect breaker. The incoming neutral cable attaches to the main lug on the neutral grounding terminal bus bar. In the main service panel board, neutral grounding terminal buses must be connected together, usually by a wire or metal bar called the main bonding jumper. In subpanels and all other locations downstream from the main service panel, the ground and neutral components must be electrically isolated from each other. Next is going to be the subpanel. So if that previous panel was now connected into this panel on the left, a new panel board should not exceed 80% of its full capacity, which means that it should have open slots for future additional circuits. However, an older panel board may not have room for additional circuits, and a panel board may be added. Subpanels or additional distribution panel boards are typically powered by a double pole breaker in the main service panel board with a 4-wire SER feeder cable that carries 2 hots, 1 ground, and 1 neutral conductor. Take a look at the subpanel illustration from the Journal of Light Construction, where there is a 4-wire SER feeder cable from the previous main electrical panel board. In a subpanel, neutrals and ground wires are kept separate and are terminated into separate bars. The tie bar at the bottom of the panel board must be removed in order to separate the neutral bus and the grounding terminal bus bar. Only the grounding bar is bonded to the panel's enclosure using the main bonding jumper. In this subpanel, the neutral conductor is the insulated neutral wire on the right, and it is connected to the neutral bus bar, which must be isolated from the enclosure cabinet. The bare grounding wire feeder conductor is on the left, and it is connected to the grounding terminal bus bar, which must be bonded to the enclosure cabinet using the main bonding jumper. At a subpanel, branch circuit ground and neutral wires are connected into separate bus bars. They should not be connected to the same bus bar in the way that they are at the main disconnect. This is a common wiring mistake. The subpanel must be equipped with separate ground and neutral bars, but only the ground bar should be bonded to the panel enclosure. Subpanels or additional distribution panels cannot have the grounded conductors, which are the neutrals, and the equipment grounding conductors, which are the grounded bare grounding wires terminated together. The ground conductors and the grounding wires must be separate in the panel. All right, let's take a 10-minute break. These questions you guys have while we go through here. The main breaker is 150 amps. That's not the service amperage. So Jeffrey, talking about if the main breaker is 150 amps, that's not the service amperage. We're talking about what the slide was trying to portray was that, yes, that might be the service amperage, but that might not be correct. So if the wire gauge does not match, if say you have a 60 amp meter outside, then that 60 amp meter, that's actually your main service amperage. So I think in what I had stated earlier is the issue that we had at my company was that, yeah, we had 150 amp service outside, or 150 amp meter outside, but we had a 200 amp main disconnect on the inside. And so technically the main service amperage was 150 amps because that 200 amp breaker was oversized. It should never been installed. The panel is allowed to be in a laundry room with a dog station. So there has to be a minimum distance away from, so if the laundry room is very large, then potentially you could have the panel on the opposite side of the room. But I would have to look up the exact distance that it had to be. So I'm not 100% sure on the exact distance that it has to be, but it could be in the same room, but the room would have to be very large. So I think it has to be more than 6 feet because the 6 foot rule, you could potentially still, the issue is touching, being able to touch or have something in proximity to a wet area, compared to the panel cover. So I will take that back and I will get the exact distance for you, Richard, and we'll find that out. I would say 6 feet would be at least the minimum. Eric Foster, how do I determine the age of the panel and relevant to code, GFI required and or AFCI required? So you have to use multiple different ways to do that. So if you look at a panel and it looks like it's been updated. So sometimes on the interior of that panel, you can find where it says, according to 2021 NEC or something like that. You have the potential that a panel could have that designation somewhere in that really tiny writing. So I would look for that. But if you think that maybe the panel was installed at the same time as a specific device, if you can figure out or you anticipate that that a device was installed at the same time as the panel, or that you don't know for sure when the house was installed or when the house was built, but maybe all the appliances were installed or that HVAC was installed at the same time. So you use those dates, which are defined, in their model number and their serial number. Then you can figure out close, when that breaker was installed or when that panel was installed. So you have to just use clues. So you have to, because a lot of times on panels, sometimes there's not a defined date on them. how much can the total, let's see, I must go down here. Okay, so Kenneth Blair, when do we report double tap neutrals and not? The question refers to age. So we'll get to this a little bit later as far as double tapping. So technically double tapping was never allowed. Now, and we'll go over the exact date here later, but it was explicitly defined in the NEC that double tapping was not allowed at a point that we'll go over later. So typically, you could say definitively that neutrals were never allowed to be double tapped, but it was only explicitly defined in a specific code year. So it's up to you on how you want to do that. Basically for me, any panel that's older than 30 years, I recommend it to be looked at by an electrician. I'm not recommending any repairs. I'm not saying the electrician necessarily needs to come out during the transaction, although it would be ideal. But any panel older than 30 years, the technology and the electrical requirements has changed so drastically in that time that that it would behoove the customer or the buyer to have an electrician look it over and see if too many circuits, if they can do a load calculation and see if too many circuits have been added during that period of time. I mean, I saw a 100 amp panel the other day that had multiple double where you have 240 volt with 4 disconnects on it, and there was multiple of those in the panel. We had flashing lights, we had dimming of switches whenever the AC unit would trip on and stuff like that. So it's definitely your call, but typically double tap neutrals was never actually allowed, but it was only explicit in the specific unit. Same thing for anonymous. How much can the total amps of the circuit breaker exceed the total amps coming to the panel? That can really only be done by a licensed electrician, because they are going to do a load calculation, because every motor that is installed in a home takes a certain amount of draw when it first starts up, but it's generally not the maximum amperage allowed for that unit. So there is a little bit of leeway in there, but that allows for the motor to age, because as a motor ages, it's going to draw more amps as it gets older. So that can really only be done by a licensed electrician. Hit a couple more of these real quick, and then we'll get back to the slides. You think it's ideal to mention about insurance companies? They have their specifications. I would not mention about insurance companies, but I do have a comment in my report that and now, as I was stating before, we're still installing 100 amp services on new construction in my area, mainly I think to save money for builders. And so I have a recommendation in there, again, that they might consider after they move into the home, that if they experience any dimming of lights, especially when an AC system kicks on, that they consider updating their service to at least 125, 150 amp service, because there are so many electronics that are in a home these days that is not being taken into consideration when just 100 amp service is being installed. I've seen many panels 6 to 24 inches above the floor and call out before evaluated either by, generally you don't want a toddler to be able to go up to a panel and open it up and start flipping stuff. So yeah, anything that's not at minimum distances above the floor should be called out. So the Cutler hammer breaker that can be double tapped. I wish I had one, but you wouldn't be able to see it on the camera anyway. Those Cutler hammer, it will show you, and maybe we have a picture of it in this slide, but it will state if it'll show you that there is, and on the little diagram on the breaker right below the switch, it'll have like a 2 copper where it'll look like 2 wires, and it'll say CU next to it. And it'll have a 1 AL next to it, which is be 1 aluminum. So you have that option, and a lot of times in those breakers, you can see where there'll be two places for a wire. Generally, any breaker that is rated for 2 wires is going to have 2 places for a wire. It's not going to just have one lug or one plate. It's going to have maybe a lug that has a bend on both ends of that plate for 2 wires to go in. That is almost, I think, the only time that you will allow for 2 wire. All right, so Kurt wants me to talk about interlocks. So interlocks are just now being required. Interlocks should be on in a panel that allows the panel or allows the breaker to be held open, allows it to be disconnected or turned off, so that if a contractor is working on say a HVAC unit that is in an attic or in a crawl space, then there'll be an interlock or a safety latch or a safety lock or some way to make sure that the breaker is turned off, that power cannot accidentally be turned back on. Okay, all right, we're gonna go back to the slides here. All right, inspecting panel boards, part 1. Electrical panel boards, regardless of their purpose, could be inspected for the following safety-related issues. Any deficiencies should be reported as in need of further evaluation. Workspace and access, missing knockouts, missing bushings, moisture intrusion, contamination, rust, signs of arcing, overheating, incorrect dead front screws, missing panel listings. So if there is no panel ratings on the board that maybe somebody pulled off the sticker or marked it up or whatever, that is that you really need to have that information available so that the manufacturer's installation instructions can be properly followed. Breaker identification, damaged breakers, missing grounding and bonding. Panel workspace and access. All electrical panels should have adequate workspace and safe access. This is for servicing, repairing, inspecting, and using devices in the panel. Panel boards should be on a secured wall space, not less than 30 inches wide, have 36 inches of space in front of them, and have 6 feet and 6 inches of headroom. The panel is not required to be centered in the space. In older homes, it is common to find electrical panels inside closets. This is no longer acceptable in modern construction. Similarly, service disconnects and distribution panels are not allowed in bathrooms. The home inspector may observe installations that are either restricted by storage items or other systems that have been installed in front of the panel. It does not matter when the house was built or that this was built to code back then. These are all major safety issues. There should be no opening into the panel interior. This is to prevent accidental electrocution by someone being able to put a screwdriver or a finger in the panel and touch a live component. However, inspectors frequently see holes where wiring has been changed or where breakers have been swapped around. All of these should be reported as safety defects with repairs by a licensed professional recommended. See this all the time. Panel knockouts with just the wire going through without a bushing, a plastic bushing or a wire clamp. And that goes for any device that electrical goes to. So I just wrote up a report yesterday where the electrical wire was going right into the bathroom fan with no bushing or no clamp. Same thing with your garbage disposal. There needs to be a clamp or a bushing. And obviously the same thing with the panel. And all that is to make sure that if, say, under the sink with the garbage disposal, if you put a bunch of stuff under that sink and you're pulling stuff out and it happens to catch on that wire, that wire just doesn't come out of that utility. And now you have a hot live wire that could cause arcing or electrocution or whatever. So all electrical wires must be connected and secured into every device. Double tapping hots and neutrals. So we were just talking about that. The practice of attaching more than one conductor to a single breaker, known as double tapping, is generally discouraged due to safety concerns. However, there are certain breakers that are specifically designed to safely accept more than one conductor. These breakers are often referred to as double lug or multi-wire breakers. One manufacturer known for producing such circuit breaker is Square D. Square D offers certain breaker models, particularly with their QO line, that are UL listed for 2 conductors. These breakers are specifically designed with dual lug terminals, allowing for the secure attachment of two conductors. The top middle inspection image show the square DQO breaker with labeling that indicates the breaker type, the number of conductors permitted, and the conductor sizes allowed. Some breakers are designed to accommodate two wires. Typically, these will have a loose plate under the screw with two slots or grooves, as we described before. The primary reason double lugging or double tapping is not permitted is that the connection is not designed for two wires, and because of this, one or both wires may not be securely installed, which could lead to arcing. This insecure installation of more than one wire at the breaker could lead to disconnecting circuit or micro arcing, which could damage the wire and the breaker. Two heavily used circuits installed on the same breaker might cause overheating at the breaker or cause the breaker to trip excessively. Two conductors that are sized according to the chart on the side of the breaker are inserted on either side of the screw. The screw tightens the plate down, securing the wire ends. An electrician or trained inspector can determine if two circuits are on the same breaker are permitted. Additionally, the NEC specifies that the conditions under which multiple conductors can be connected to a single breaker. Home inspectors should be familiar with these regulations and specific models of the breakers that comply. All right. Oh, I think this is where we get into the double tapping neutrals. So the grounded conductors, commonly called neutrals, are the white wires inside the residential electrical panel board. Only one neutral wire is permitted to be connected under one lug of the neutral bus bar. Panel board neutral bus bars are usually not listed for use with more than one wire per terminal. These rules can be thought of as the one wire per hole rule. Neutral wires should not be double tapped or triple lugged under a lug or fastener of the neutral bus bar. Neutrals should not be combined with a grounding wire either. It is sometimes said that double lug neutrals were not prohibited by the National Electrical Code until 2002. That is incorrect interpretation of the NEC. Until 2002, the NEC simply stated that panel boards must be installed according to the UL standard, which says an individual terminal shall be provided for the connection of each branch circuit neutral conductor. The NEC has never allowed double lugging neutrals, even if it did not specifically address the topic until 2002. So there you go. An incorrect wire size or gauge is common observation by home inspector when inspecting 15 and 20 amp breakers at the electrical panel. An incorrect wire gauge may be found at any breaker. An example of an incorrect wire gauge is where a 14 gauge wire is connected to a 20 amp breaker. This is a defect because the size of the breaker to the 20 amp is too big for the size of the wire. A wire gauge that is smaller than the minimum size for the breaker is vulnerable to overheating. Oversizing the wires for the breaker is allowed, but generally not happening. A home inspector should never insert a potentially conductive instrument into the electrical panel in order to take a measurement of the wire gauge. If an inspector uses a wire gauge measurement device, it must be tested and confirmed to be non-conductive. Different manufacturers have different thicknesses of the plasticized insulation on the wire, which may make an inspector look for other clues to the wire gauge, particularly the labeling on the wire itself, which can be difficult to do. The main intent of the NEC 240.4 is to provide standard overcurrent protection of the conductors to prevent them from carrying more current than they are rated for, which could lead to overheating and potentially cause a fire hazard. The NEC has established maximum overcurrent protection ratings for certain conductor sizes, and this table translates these limitations into a format that can be easily followed. Oh, whoops. Real quick. There we go. Home inspectors can use this table to check that each circuit has the appropriate size breaker or fuse. If, for example, a 12 gauge copper wire is protected by a 30 amp breaker, this would be a defect. Since the table indicates that the maximum overcurrent protection for a 12 gauge copper conductor is 20 amps. Exceeding this limit could cause the conductor to overheat under overload conditions. All right. All right.
Hey, Heath. Hey, Cal. Wow, Professor is in. Look at your display here. Yeah, I figured it's about time to have a little lesson on wire size, or the American wire gauge that we skill. American Wire Gauge, that's what that stands for?
AWG, yes.
Funny, I was just wrong. Okay,
So you can see we have a lot of different sizes, and there's a lot of different reasons for having these. Depends on what the device is going to utilize as to how big the wire is going to be, how much power it needs.
right. So not all electricity is the same when it's running through our house?
Right, we can't just run one size wire to feed everything in.
Okay,
So it starts off with these smaller numbers and it actually runs backwards till it gets to a certain point down here, and then it starts climbing again.
so let's start with the smallest.
So this is 18 gauge, and in this case, it's a thermostat wire. And we have 4 conductors, each conductor is 18 gauge, so that one right there is 18.
Okay, so something like that used for thermostats, doesn't require a lot of power, sufficient.
Control.
All right, moving up from there.
So next step is 14.
Mhm.
This we'll see a lot in the house, and the color kind of helps us identify it in newer homes. This we're going to see for loads like lighting, bedroom receptacles, that kind of.
Basic, predictable,
Right.
no problem.
Yeah, and you can see it's a little bit bigger than that 18.
I have heard you throw around 14.2, 14.3. That refers to what?
So that refers to the number of conductors. So the first number is the gauge size, that 14 that we can see. But then the 2 would be, we have 2 conductors and a ground. So 1, 2, and our ground. That's our 14.2.
And so there might be a third conductor if you have that 3-way switch or something like that.
Exactly.
But it's still the same size.
Same size, just more conductors in the jet.
Okay. Also familiar with this. You seem like we always run that in the kitchen and other places.
Kitchens, your washing machines, sometimes in the basement, bathrooms. We want that larger size, that 12 gauge that can handle 20 amps.
Because we're going to be using appliances that pull more electricity, a dishwasher,
Exactly.
blender, something
So those are
like
the
that.
areas we're going to have coffee makers, toasters in the kitchen. Needs a lot more power. Want to have a larger cable that can handle it.
Mhm. We've talked about GFCI receptacles before. They
Mhm.
always are attached to something like this. Just out of curiosity, do we ever put a GFCI protection on this?
Or we can, if it's providing power for something in the garage, in the basement, absolutely, there's no problem putting a GFCI on it.
Cool. Okay, so moving on to the orange.
The orange, 10 gauge, 30 amps typically in a residence. Dryers, maybe your outdoor air conditioning unit, maybe a small oven in the kitchen, stuff
That you know is going to pull a lot of
that's going to
electricity.
draw a lot more, correct?
So let me just ask you, what if I start using the wrong wires? Or what if I start trying to plug things in with maybe the 14 gauge that I should?
That shouldn't.
Yeah,
So what's going to happen is certain appliances use a certain amount of power. So if something's really designed to be used in the kitchen or a bathroom, you want to try and plug it in there. If you try and plug it into a bedroom circuit that's a little bit smaller, it may draw too much current. It may overheat the wire, it may draw too much from the breaker and cause them to trip. We don't want to have an overheating issue where we're plugging something in the wrong place.
so don't bring the blender into the bedroom.
Please.
Okay, this guy here?
So that's our 8. We're going to see this maybe for some smaller ovens, air conditioning units, that kind of thing as well.
Right, and then 6s?
This might be one of the last ones you'll typically see in the basement of your house if you're looking around, or if you open up some of the walls. We're going to use this for an electric oven, maybe a level 2 car charger.
Gotcha. So that means that from like this point on, this is sort of more big boy stuff here.
Right, now we get to the single conductors, and this is where we're going to install these, typically on conduit, use it for a larger load. Maybe we're feeding a hot tub outside. Maybe we're feeding a subpanel in the house. That's where these are going to come.
So that's interesting. You call them single conductors. So, you know, at first glance, this looks a lot bigger than this.
Right.
But to your point, there's only one of these copper conductors. So we're comparing that
To this.
just to one of those.
Correct. So this is a jacket with multiple conductors. This is just our.
Okay. So when do we use things like this or this?
So this is something much larger. Something like this, or even this. This is 500 kc mil. This is the size. So if we really want to confuse the numbers, we go backwards till we hit 1 up, start going up, and then we go metric.
AC, oh, the letter K.
Yep, 1,000 circular millimeters.
Gotcha.
So this would actually carry 400 amps.
And so why would I use that?
If you had a really large residential service, and it's a little unusual, more of a commercial or industrial application.
Right.
For a 200 amp service in a home, though, if we're doing copper versus aluminum, we're going to use this 300.
So headline here, right wire for the right usage,
Right.
for the right appliance or service.
And you'll be good.
Well, next time we're going to talk about volts and amps, but this is enough for now, Professor.
Sounds good.
Thank you.
AC breaker size. Let's see, the home inspector should know that the IRC and the NEC provide exceptions to the general rule of overcurrent protection ratings of breakers and the connected wires that are only for air conditioning and heat pump equipment. Branch circuits for the air conditioning equipment and big motors may have an overcurrent protection device rating that exceeds the conductor ampacity, and this is not a defect or an electrical violation. The 2021 IRC states that air conditioning and heat pump equipment circuit conductors are permitted to be protected against overcurrent in accordance with section 3702.11, which says that the branch circuit overcurrent device rating must be the size and the type marked on the appliance. To determine the maximum size of the overcurrent protection device and the minimum size of the conductors for the air conditioning and heat pump equipment, the inspector has to use the data on the equipment nameplate attached to the unit outside. The overcurrent protective device rating for the air conditioning condensing unit and the heat pump circuits is stated on the equipment nameplate with a minimum and maximum rating given. The nameplate will also state the minimum circuit ampacity for the branch circuit conductors. The home inspector should know that the IRC and the NEC provide an exception to the general rule for overcurrent protection ratings of breakers and the connected wire sizes. And knowing that exception and applying it will help home inspectors do better inspections. For example, if a home inspector observes a 50 amp AC breaker on an 8 gauge wire, that may not be a defect. It might be okay and likely not a defect, even though the breaker will be sized larger than what the inspector thinks is permitted. Now, that does not include the maximum breaker amperage on the exterior unit, on the exterior AC or heat pump unit. That breaker must match those breaker ratings, the minimum and maximum. The breaker installed must be within those two, but what we're talking about here is wire size. All right, before even thinking about touching, inspecting, or removing a dead front, the inspector should look carefully for signs of water, moisture staining, or rust on the panel or its surrounding wall. As we saw with the service entrance, any failures of the master cable entryways may result in water getting into the panel. Yeah, you see anything relating to water in or around that panel, recommend a licensed electrician. Contamination. So newly installed panel boards should be covered with protective sheeting temporarily while the electrical contractor is installing the rough wire above it. Otherwise, unprotected panel board and its components could be dirtied by dust and debris. Another example could be when the panel board is installed and the drywall contractor uses a router to cut openings for electrical boxes or fixtures. The drywall dust could enter the uncovered panel board. Another example of an unprotected panel board could be when the bus bars might be coated with paint while the walls were being spray painted. There should not be any paint or wall texture sprayed on the wiring, connections, or buses inside the electrical panel. The general consensus is that any contaminant that cannot be removed with a dry cloth is considered a defect. Coordination between the construction trades is needed to prevent these types of problems and is required by code. Nests from pests such as bees or mice should be reported as in need of correction. Foreign debris of all types should be removed from the equipment. There should not be any damage to the components of the electrical panel board, inside or out, that might adversely affect its safe operation or the mechanical strength of the equipment. Parts of the panel board and its components that are broken, bent, cut, or deteriorated by corrosion, chemical action, or overheating are all defects that should be reported as in need of correction. Do not touch a panel board or any electrical component or system that shows indications of rust and corrosion, burn marks, arcing, scorching, or anomalies of any kind. The inspector must maintain the safety when performing the inspections. Stay safe, keep yourself safe, and keep your clients safe. Where you'll see a lot of rusting is if you ever have a panel anywhere near pool equipment or pool chemicals. If you go into a pool house or into a there's a utility closet on the outside that was intended to be for an electrical panel board or distribution panel. And a lot of times homeowners will just throw all of their pool chemicals or their hot tub chemicals in there. Well, those chemicals get into the air and then they mix with the moisture in the air and then they corrode horribly the metal enclosures and anything that's metal in them. Not just electrical components. As part of the initial visual inspection of a panel, the inspector should look closely for any signs of arcing or burn marks on the panel. These may be the result of previously repaired problems, but don't rely on that being the case. Also, take a second to listen to the panel, because many times you can hear arcing. Arcing or smoke damage on the outside of the panel is obviously indicative of a previously significant and dangerous condition. It is recommended that the inspector, at minimum, ask the homeowner for details of the damage and its repair prior to opening the panel. Remember, there are many issues that can lead to this kind of telltale marking, and many of those can lead to the panel board being live or short circuits being caused by removal of the dead front. Yeah, I have taken was taking a panel cover off, and you get sparking, out of the screw hole. So obviously, at that point, you just call an electrician. There's a safety hazard there. Or call the seller's agent, call your agent. Make sure everybody is aware, and that they get an electrician over there as soon as possible. Edison-based fuse panels were universal from the earliest days of electricity in the American home right up until the 1950s. Many homes built up until the late 1960s still had fuse panels. Many insurance companies, however, will either not insure homes with Edison-based fuse panels or will insure them at higher premiums. This is not due to any danger, but rather it's just shows that they are older, unimproved system, and more likely to have an electrical fire, especially for if homeowners have not used the fuses correctly and put pennies, short circuited or shorted out the fuse itself to ensure that their electricity stayed on. Many fuse style panels use a fuse block as both the primary overcurrent protection and also as a disconnecting means. These are shotgun shell fuses. These blocks must be pulled to disconnect the power from the home. These fuse panels are normally rated either 60 or 100 amps. You will also see these in old HVAC disconnects. Many homes from the 1930s onward used main and range panels. These have two fuse blocks, one acting as the main disconnect and primary overcurrent device, and a second block supplying power for the electrical ranges. These became very common from this time on. Some fuse panels may contain as many as 4 fuse blocks, commonly having one as the main disconnect, with the other supplying other 240-volt circuits for appliances such as ranges, air conditioning equipment, clothes dryers, and either other distribution or subpanels. And a lot of times, none of this is labeled, so you don't know what fuse goes to what device or which one is your main. There's a lot of confusion when it comes to these guys, and you'll see these in subpanels too. A lot of older subpanels that you'll see in bedroom closets. Let's see, these are the fuses that screw in, Edison base or plug fuses. So it's very common to see overfused circuits on older fuse panel installations. The inspector needs to remember that in most cases, the installation was designed to supply a relatively small number of circuits with relatively few receptacles. That would have been fine for the average family's needs in the 1950s and 60s, but that's now exceeded by modern demands. Several types of fuses are available. Some blow very quickly, while others are designed to cope with short or extra startup loads associated with electric motors. These will blow after a short time if the amperage draw does not revert to normal levels. S-type fuses also have the added benefit of stopping someone from repairing a blown fuse by putting a penny under the blown fuse in older practice. You can see that, I don't know if you can see this in the hand, but this is an old Edison base style fuse panel. So all of the fuses that are in there, there's 15s, 20s, and 30s. They can all be placed wherever you want. This definitely can lead to major electrical issues. Inspecting fuse panels. There are two major problems with inspecting older fuse panels. First, check the main fuse amperages. The blocks have to be pulled out, which shuts off all the power to the home. The second issue is that these panels tend to be unsuitable for modern high amperage demands, and they tend to exhibit double taps and overfusing. So what to look for? Main fuse rating, are there double taps? Rating for the fuses match the conductors. Are they updated to the S type, which have these different sizes of bases instead of the general base? And is there any signs of overheat? All right, the dead front screws are important to check. Some inspectors carry with them a small bag of screws designed to replace the missing or incorrect screws. When screws penetrate through the wire jacket, an arc flash vaporizes the steel of the screw and the panel or the copper of the conductor and can set a cloud of molten metal and sparks straight out. That's why the inspector needs to be wearing safety glasses and cotton clothing. No polyester or any type of plastic type shirts. All panel boards are required to have an accurate listing of what the circuits are connected to. And panels, like any other components, are rated with a UL listing, and that listing should be, should have all of its panel rating information on it. Panel bonding. In all cases, look for a green-headed screw identifying the panel is bonded to the ground, and make sure that, depending on if it is a main panel or a sub panel, that it is, you're looking for the correctly isolated or the correctly bonded and isolated neutrals and grounds. Problem panels. Here we go. This is some of the interesting stuff. The Pushmatic, which you saw a video of earlier, the home inspector may come across these very old panels. There's other panels that are problem panels include Federal Pacific electric panels and Zinsco Sylvania panels, and then your split bus panels. The problem with Pushmatic is that the breakers would stick or would not trip correctly. So if you ever see a panel that has the push button instead of the switch, you need to call that out. There's a general consensus among electricians and many industry experts that some electric panels have significant safety issues like FPE, Federal Pacific, Stablock, Zinsco, GTE, Sylvania, Bulldog, Pushmatic, and Challenger. The problem with FPE panels is primarily with their Stablock panels and breakers. These are featured stamped sheet metal or copper bus bars and breakers with thin copper tabs that were designed to lock into the bus. These have a hazardous tendency to fall out when the dead front is removed. This can be a shocking surprise to many home inspectors. The recommendation for these panels is to replace the electric panel board. There are no recalls on these panel boards, with the exception of approximately 1,000 Eaton Cutler hammer panels in 2014 that were built on the Challenger design. The inspection images, well, you can see you have the stab lock. The first one is the stab lock. The next one is the loose breakers in the stab lock, and then the other right side is the Challenger panel. Home inspectors may receive criticism from unhappy sellers and even from some electricians about the need to replace these panels. The two common arguments against replacement are it's working just fine, or the old breakers can be replaced with new aftermarket breakers. No one can know if it's working just fine until it's under stress. One of the significant issues with FPE, Zinsco, and Bulldog panels is that the breakers fail to trip with overcurrent shorts or ground faults at rates far higher than the industry standards. In actual testing, breakers in these panels may trip correctly a few times before failing. Other issues with these panels are that breakers can fatigue over time, becoming loose on their buses, loose connection, overheat, or even melt. Most, if not all, aftermarket replacement breakers are not UL approved and cannot be considered reliable. Some aftermarket breakers are incompatible despite their advertising, such as aftermarket Pushmatic breakers. Using other branded breakers that may fit the bus is not an approved repair or considered safe. Complete panel board replacement with the most modern equipment remains the best recommendation. Note that in most areas, replacement panel boards are not required to meet all of the latest code requirements. If there is a need to modify or extend the old breaker panel to include modern AFCI breakers, the older panel boards may not be able to accommodate them. A home inspector should know what the local community or state requires. Oh, here we go. The earliest Zinsco panels had buses made of copper bars and were very reliable. However, during the copper shortages of the mid-1960s, copper was replaced with anodized aluminum bars. This led to problems of poor contact between the breaker and the bus bar, and many have failed since due to arcing between the components. The problems continued after Zinsco's sale to Sylvania in the early 1970s. And you can see here all the issues that occur. When home inspectors see a split bus panel, they should count how many throws are required to turn off the panel. More than 6 throws are usually found where someone has added a circuit to a full panel by adding a double breaker, tandem, or piggyback breaker on the upper bus section. Installing an additional 120-volt breaker in the top portion of the split bus panel is likely a defect. The breaker may not be listed or approved for that panel, and this changes the number of disconnecting throws from 6 to 7. So that's a defect. Three-phase power supply is common in commercial agriculture and some apartment properties. Evaluation of these panels is well beyond a home inspection and should be deferred to a specialist commercial electrical contractor. While we are not going to explore in depth the methods of evaluating three-phase supply, some knowledge is useful to the home inspector. Three-phase supplies have 3 hot or ungrounded connectors, and there may also be a neutral or ground conductor. Each of these phases or legs carries 120 volts at a different phase from the others. How and from where power is taken in these phase supplies produces different types of supply current. The common services include 120, 240, 208, and 480. In three-phase panels, the conductors are color-coded to identify which phase they're attached to using black, red, and blue. While there is no required standard of color coding demanded in the NEC, the code does tell us that on 120 or 208 delta high leg system, the center B, the 208 volt to ground, should be marked with orange tape to identify it as the high leg. These legs can supply 120 or 240 volts, as one would see in a standard 120, 240 volt residential supply. So it is possible for the average inspector to evaluate some electrical branch circuits in offices or other non-industrial settings, but beware of evaluating the distribution panels themselves. Panel anomalies. The home inspector may occasionally see some very unusual panels, oddities, or anomalies in the home. Some panels are now obsolete or just plain dangerous. 100+ years ago, when we started wiring homes for electricity, there were no standards for panel enclosures. In fact, if an early panel had any kind of enclosure, it was probably built on site from timber and had an asbestos lining. Even today, some homeowners will build a distribution center without the benefit of protection of a listed enclosure, as that really grainy picture on the right shows. The problem with fused neutral panels is that the neutral fuse bus blows instead of the live fuse blowing, and then the circuit will appear to not be live. However, someone working on the system would easily be able to complete the circuit to ground, providing a return path for the current and thus be electrocuted. Non-metallic panels. Wood enclosures were very common at one time, but other materials have also been used, especially plastic. They never achieve significant market share, but you might see them, especially on subpanels in garages, stuff like that. Non-rated enclosures, homeowners DIYing their own electrical panels. Just, if you ever see that, recommend an electrician. NEC requires a distinct separation of low voltage wiring and high voltage wiring. Very common to see garage doorbell transformers inside panels. Those should always be removed from the panel. Same thing kind of goes for surge protectors, lightning arresters, all that stuff. Now, some lightning arresters might be rated for inside the panel, but surge protectors are not. Here's a very extensive checklist. So just take pictures, lots and lots of pictures. Wear your PPE, especially if you're going to remove the dead front of any panel. And then, use the back of your hand to touch the panel. Make sure you're not getting any tinglies, and/or use your non-contact voltage detector and run them over the panel cover. I've never experienced it in a residential home, but I've experienced it a lot in commercial properties where the panel cover has been energized, especially on something that's been abandoned for a long time. Make sure you have adequate space for work. Make sure there's adequate space in front of the panels. Identify breakers in the off position. This is very important, and you never want to turn on a breaker that's in the off position. You know, if you don't know, or the homeowner isn't there to tell you why a breaker is off, then I would completely refuse to turn a breaker on. That goes the same thing for new construction. A lot of times they'll not, they'll not have the water heater active, or not have the AC unit active, or whatever. So I would not recommend turning on any breaker, because you don't know why it's been disconnected. Installation might not be complete. There might be a known defect. So if you turn anything on, you are now responsible for whatever happens. So if you burn out a unit, or you start a fire in the house, or whatever, it is not in any standard, no state standard, and definitely not InterNACHI standard to turn on any breaker. So do not, and you will have realtors hound you for sure. They'll ask you, oh, I had a realtor got so mad at me. I made a seller's agent. The house had been abandoned for a long time. I refused to turn the breaker on to the house, and so she had to drive 45 minutes and turn the breaker on for me. And luckily she did, because we had, now there was no damage associated with it, but I didn't want to start a fire. I had no idea why it was in the off position. And definitely anything rusting or corrosion. If there's water there, or there's rust there, a lot of times the inside is rusted, and there could be a multitude of issues that you run into removing that. And then if it is rusted, or you remove something, and then maybe you can't get the panel cover back on, you just created a whole new issue. And definitely, any scorching, melting of wires, any black marks inside the panel. If you do take the panel cover off, that everything was good, and you do pull that off, that is now, if you see any arcing, any melting, anything like that, that is now a safety issue. If you ever run into any safety issue where the occupants of the home are not obviously aware of that issue, then you need to make everybody aware that there is a fire hazard, because the last thing you want to happen is you leave that home, and because you change stuff in that home, and you did not, and you found some safety hazards, you found some issues, and you did not tell the seller's agent, or your buyer's agent to tell the seller's agent, you'll catch that blame if anything happens. So make sure everybody's aware, and document. Checking for solid conductor aluminum branch wiring. Obviously, we have stranded aluminum branch wiring, but if there is any solid conductor aluminum branch wiring, definitely want to identify that. Now, there is tin tinted copper wire, and those are, I would say, those are very difficult to identify, solid aluminum versus tinted copper. So just pay special attention, and when in doubt, refer to a licensed electrician.
Now we're gonna look at 3.7, which is the electrical system. It starts with your service. So on this house, we have an underground service. It's actually marked right there because they had somebody mark the yard. First thing we want to do is pull on our meter tag. If it comes apart, or if it's cut, we want to write that up as a defect. You can tell somebody's painted one and not the other. It makes me think at some point this has been replaced. Looking, our nipple there, we have wiring run, looks like over to the garage in conduit. We want to make sure that's always in conduit. Open this up. We want to make sure we're not too high above the ground. Now, looking at this, looks to me like we're missing some of our legend. 1, 2, kind of mismatched. So I would write this up. One is missing a dead front cover screw. Missing or not labeled completely. Now remember, we wanted to look at the air conditioner, see what our data tag was, to see if we had the right breaker. A 5 amp, that was rated for 20 to 40, so we're okay. Now, standards of practice, we are not required to open a dead front cover, but we are allowed to open a dead front cover. So typically, this is how we're going to tell what our service wires are,
what our 120 wires are and what our 240 wires are. So if it is safe and you are comfortable, it is always best to open up the dead front cover. There are a few states and jurisdictions that do not allow home inspectors to do this, however. So you need to check with your local jurisdiction and your standard of practice for your state. Remember, safety is always priority. There's more items in an electrical panel to report on than anywhere else in the house, but it also can be very dangerous if you're not careful. Now, normally we put on gloves and wear shields. For the video, that doesn't work so well. So today we're not doing that. But just understand, you do want to wear your protection equipment. If I put it on, it's really hard to hear me talk, things like that. So we open up the panel. First thing we're going to do is take some pictures. Now, typically, we wouldn't see this by an electrician, this extra insulation. We are required to have at least a 1/4 inch. So this is not a technical defect, but it just tells me we've had people in here that probably weren't an electrician. We're going to look, what are our service wires? Aluminum. What are our 120s? Well, I'm seeing a lot of aluminum 120s there. Now, when we point, I either use my plastic stylus, or a lot of times we will also have a plastic pin. So if I'm going to show my clients a problem, I'm going to point to it like this. Don't use a screwdriver. You shouldn't get in the habit of using your finger. If you do, stay a long ways away. But a pin works really good. So I'm going to say most electricians wouldn't leave this much insulation. We're using what's called fused neutrals. We have a bunch of neutral wires under one screw. Most panels do not allow that after 1996. Now, this is a 1971 house. So it was acceptable, but that area is prone to bad connections. So a lot of times we'll see scorched melted wiring when they do that. Here's our grounding and neutral bus bar because it's a main panel. Here is our bonding strap. So we want to look and make sure our bus bar on a main panel is bonded to the case. Then we're going to go down and look at our breakers. Do our wire sizes correlate to the breakers? And these they do. 30 amp, 10 gauge. Here we have, that's copper on this one. That's a 14 gauge, so it's a 15. Now you'll notice these wires look really big. When you're using aluminum wiring, we have to upsize them. So a 20 amp uses the 10 gauge wire. 15 amp would use a 12 gauge, unlike copper, which would be 12 or 14. So we want to look, make sure all the breaker sizes are correct for the wiring. We're going to come over here and look, do the same thing on this side. Now these are 15s, so these are 12 gauge because they're aluminum. 10 gauge, 25, that's okay. This is another copper wire, so it's 15 and 14, that's okay. And up here, 50 for the range, that's okay. So we have aluminum service wires, we have copper and aluminum for our 240s, and we have copper and aluminum for our 120s. So that goes in your report. Now, whenever we see aluminum wiring on our 120 circuits, you do want to call it out for further evaluation by a licensed electrician. We have had a lot of problems with aluminum wiring. So now they typically either recommend replacing the wire or redoing all the terminals with either copper imprints or Alumicons. So,
all right, guys, we're gonna stop old Jim here, and we're gonna keep busting through. We got some more slides to get through before the end here. So let me switch back over. And all right. Wiring types. You can see we typically see NMB cable, SE cable, armored cable, and underground feeder. I think we've kind of gone through some of this before. The NM cable is non-metallic, which is what we normally see. Conductor material. We got copper. I talked about tinned copper. Still sometimes seen on older properties. Copper is tinned for 2 reasons: to aid in soldering and to stop copper from reacting with the old rubber insulation. Yeah. Um, let's see. That was tin copper on that bottom. So like I said, if you suspect tin copper, try and look on the end. Look on the end of the exposed conductor, and you should be able to see that brown tint, which shows you that it is a copper conductor and it just tinted, which makes it look like the outer sheathing is aluminum. Knob and tube. Knob and tube. Knob and tube wiring is so named because of the porcelain fittings used to support and insulate the conductors from the timber components in the home. The knob holds the wire away from the rafters and joists while the tubes are inserted into holes, bored through joists and studs to protect the conductor and its rubber insulation. Knob and tube wiring was common method used to wire homes in the United States prior to 1930. Knob and tube is a two-wire system with a hot, ungrounded, and a neutral, grounded conductor only. No separate ground is used, so all receptacles would have to have been two-prong only. The home inspector should report any knob and tube wiring as in need of further evaluation by an electrical contractor, due to the following reasons on the slide. Armored cable, not going to see a whole lot of this unless you're in a commercial property. Exterior flexible conduit. This is often seen to supply air conditioners. Now, it used to be where because the exterior flexible conduit, if it was armored and it had a metal also on the outside, that the metal would maintain the continuity from the disconnect to the unit, and that would maintain the grounding or the bonding. At least that's what the concept was here. That has had since been gone away because a lot of times those connections become loose and that continuity is then compromised. So they no longer allow for armored flex cable to be used to maintain the bond for the electrical system. Rigid conduit, again, we're not going to see a whole lot of this stuff in residential, but oftentimes it is beautiful workmanship. It's good to see. NM cable, non-metallic cable. So many people use the name Romex when referring to NM cable. Romex is the trademark, just like Kleenex is for tissues. The earliest cloth wrap MN cables were originally approved by the NEC in 1928 as a replacement for knob and tube wiring. It became the most common residential wiring used from the 1940s up to the introduction of the modern thermoplast Romex type wiring in the early 1960s. Prior to 1985, standard NM cable was rated for 60-degree applications, which was increased to 90-degree and is now marked with NMB. The type NM cable conductor insulation is color-coded for identification, typically one black, one white, and a bare grounding conductor. The National Electrical Code specifies that the black conductor represents the hot conductor with significant voltage to earth ground. The white conductor represents the identified or neutral conductor, near ground potential, and the bare green conductor, the safety ground conductor, not normally used to carry current, circuit current. You will sometimes see where a white wire is installed on a breaker as a hot. That just has to be identified on both ends. So wherever that's going, it's not ideal, but you will see it. UF underground cable, and we talked about that earlier. Aluminum wiring. Between 1965 and 1973, single-strand aluminum wiring was sometimes substituted for copper branch circuit wiring in residential systems. After a decade of use by homeowners and electricians, inherent weaknesses were discovered in the metal that led to its disuse as a branch wiring material. Although properly maintained aluminum wiring is acceptable, aluminum will generally become defective faster than copper due to certain qualities inherent in the metal. Neglected connections in outlets, switches, and light fixtures containing aluminum wiring become increasingly dangerous over time. Poor connections cause wiring to overheat, creating a potential fire hazard. In addition, the presence of single-strand aluminum wiring may void a home's insurance policies. Inspectors may instruct their clients to talk with their insurance agent about whether the presence of aluminum wiring in their home is a problem that requires changes to their policy's language. There's your general issues with aluminum. Less ductile, higher electrical resistance, galvanic corrosion, oxidation, greater malleability, greater thermal expansion and contraction, and excessive vibration. Aluminum wires are the color of aluminum and easily discernible from copper and other metals. Look for AL or aluminum on the jacket. And if the house was built between 1965 and 1973, are more likely to have aluminum wiring. Options for correction. I think we heard Jim talk about that a little bit. Replacement is always the best, but the only true replacement option is called the Alumicon. Which crimps the aluminum connector again. Oh, I'm sorry, not Alumicon, cope aluminum connectors. That's right. Sorry, that's the one. That's the slide. So other repairs just do not last. So you can see the proper repairs in the bottom right-hand corner of this slide. So this is your general breaker fuse size with their copper conductor that you can see there. We kind of went over some of this stuff. Guys, I'm going pretty fast here because I have like 70 more slides, and obviously we are short on time. So neutral sharing, we kind of already talked about neutrals not sharing lugs. If the conductor is damaged at all, where it's been cut, where some of the braids have been cut, or where the outer jacket has been scored by the wire cutters when the electrician was installing that, all of those are defects. Anything that compromises the intended continuity of the conductor is a defect. Grayish paste is commonly found on older aluminum multi-strand conductors. Like I said, sometimes it's not required anymore, so you may or may not see it. They have new wires now that allow that to not be required. So abandoned wiring should always be recommended for removal. Arcing and overheating obviously should always be recommended for electrician, and definitely I tell the seller definitely put it in your report, but tell the buyer's agent and the seller's agent, or the seller if they're home, and let them know that they have a potential safety problem inside their home. While electrical splices and panels are not in and of themselves improper, they should bear in mind that there's a lot of issues that it can lead to. So you can pigtail, but it is not, you need to pay special attention to those pigtail locations. And if you feel like there's too many pigtails because they're trying to limit the amount of breakers in a panel, that needs to be evaluated by an electrician. Lightning damage, same thing. Any kind of damage inside the panel needs to be evaluated. Protection of wiring. Electrical splices always have to be in splice boxes with grommets or clamps to prevent the wires from being pulled apart. All conductors should be protected and secured inside attics. Inside attics and in crawl spaces. Wires on the floor of the crawl space are not allowed. Loose wires in attics are not allowed. Everything needs to be secured, mainly because if you're going in that attic or in that crawl space and you're crawling or you're walking and your foot grabs a wire and it potentially pulls the wire out of its breaker or out of its splice, and then you run into major safety and fire issues. If you have metal studs, you have to have proper protection, just like you have to have proper protection going into an HVAC metal cabinet. The vibrations and the movement can eventually rub through the exterior insulation of the wire, and you can energize the panel, or the studs, or you can energize anything that it's touching. Making sure everything is supported and stapled, nothing is loose. Splice boxes are covered. And this is a huge deal. Real quick, I know we're finishing up here, but if you ever see splice boxes, so maybe all the splices come into the splice box and everything is secured with clamps, but you're just missing that cover. If insulation gets poured on top of that, all of those electrical connections being covered in insulation will heat up over time, and it will cause a fire. We had one. We've had many of them in my hometown here, where somebody came in and blew in cellulose insulation. They ended up packing the open electrical splice boxes because they weren't covered, and then they ended up having a fire. Please email me any questions. I'm going to try some of the questions that we have here in the question and answer. We'll note them, and if well, I don't know if we can get them to you, if there's a way to get them to you, but I can answer them and send them to Kayla, and then if she can get them to you guys, or we'll figure out how to do that. But yeah, we'll definitely get all the information that you guys want.